The universe is bleeding evidence, an icy scar in the cosmic microwave background, a lopsided pull on galaxies, a pattern that should not exist. If our best maps of reality are showing fingerprints from the outside, then something has already reached into our cosmos. Are we watching another reality leak into ours? And if it's spreading, what happens when it finally touches us? We are living inside a model, and the model is starting to show seams. Not cracks in metal, but mismatches in the sky's oldest measurements. In this film, we follow a trail of signals that do not agree with the simplest version of our universe. Each one has a mundane explanation waiting nearby, and each one also leaves room for something far stranger. The question is not whether reality is haunted, but whether our maps are incomplete. When independent observations tug in the same direction, the response is to ask what they share: instrument limits, statistical luck, or a missing piece of the architecture. We will begin where cosmology is most honest, in the oldest light we can measure and the assumptions that shape every conclusion. The cosmic microwave background is not just a picture, it is a census of the early universe, written in temperature and polarization. If that census contains an outlier, the first duty is to try to erase it with ordinary structure. We will trace how a vast emptiness, a supervoid, could sculpt a cold imprint through gravity and expansion, then measure how far that conservative story can stretch. But one anomaly is easy to dismiss and a pattern is harder. As we widen the view from a single patch of sky to the motion of galaxy clusters, we confront claims that the universe may carry a coherent drift that standard cosmology struggles to absorb. Motion, however, is not the end of the argument. It is the bridge to geometry. If space-time itself has been perturbed, we should be able to describe the disturbance without reaching for superstition. We will examine how inflation could produce other cosmic domains, and what a collision would have to look like in data we can actually collect. Then we step into deeper architecture, ideas in which our universe is a surface, and the wider reality is a bulk we do not directly perceive. In those pictures, the distance to elsewhere may not be across space, but across dimensions. Next comes the most familiar stranger we already live with: dark matter. We will ask whether the hidden mass-holding galaxies together could also be a hint of a neighbouring sector, one that shares gravity with us but refuses every other interaction. And finally, we face the most unsettling possibility. If the rules of physics can change, even rarely, then the ultimate threat is not an object in space. It is a transition in the vacuum that defines what matter can be. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. From a bruise in the oldest light to currents in the largest motions, we follow the evidence outward, then inward, into the theories that could contain it. And at every step we ask what would count as proof, before we decide what to fear. Space looks calm from a distance, and the universe looks smoother still when we blur our vision on purpose. But the oldest light we can measure carries a mark that refuses to blend in, an irregularity that feels less like noise and more like a bruise. Astronomy calls that light the cosmic microwave background, the CMB, and it is not a metaphorical relic. It is the universe's baby photo, taken when the cosmos first turned transparent and the fog of charged particles finally lifted. For the first few 100,000 years after the Big Bang, the universe was a hot plasma. Electrons and nuclei moved freely, and photons could not travel far before scattering, so space behaved like a glowing, opaque furnace. About 380,000 years after the beginning, temperatures fell to a few thousand Kelvin, and recombination began. Electrons joined with nuclei to form neutral atoms, scattering collapsed, and light started streaming through expanding space with far fewer interruptions. That moment is also the origin of the last scattering surface, which is not a wall you could touch. It is a thin shell in time, an epoch, whose photons have been travelling ever since, stretched by cosmic expansion into microwaves. Today, that ancient radiation has cooled to about 2.725 Kelvin, only a few degrees above absolute zero. It arrives as microwaves from every direction, so faint that it hides behind our own galaxy, unless we measure with extreme patience. If you could see it with your eyes, the sky would glow with a uniform, ghostly brightness. Yet when we subtract the average, the leftover pattern looks like delicate grain on film, tiny hot and cold patches that encode early conditions. If the cosmos is fair on the larger scales, that glow should be statistically uniform. It should vary only by tiny random ripples like noise riding on a perfect signal, with no special direction that keeps winning. That expectation has a name, the cosmological principle, and it is older than the satellites that tested it. On large scales, the universe is homogeneous and isotropic, meaning no preferred place and no preferred direction, at least in the statistical sense. Historically, this principle grew from a philosophical instinct and hardened into a working rule. It echoes the Copernican idea that Earth is not central, then extends it. Our galaxy, our cluster, even our cosmic neighbourhood should not be privileged. Modern cosmology is built on that assumption because it makes the equations solvable, and because it often works. It underpins inflation, and it anchors the standard LCDM model, the framework that turns a sky map into facts about space. Inflation says the early universe expanded violently in a fraction of a second, stretching space so quickly that regions once in contact were flung far apart. In that picture, initial irregularities were diluted, while quantum fluctuations were magnified into the seeds of structure. LCDM says cold dark matter provides the gravitational scaffolding for galaxies, and dark energy accelerates expansion at late times. Together they explain a great deal: the CMB power spectrum, the distribution of galaxies, and the way time has unfolded since the early universe. In that framework, the CMB anisotropies are not flaws, and they are not cosmetic. They are the seeded fingerprints of density and temperature fluctuations that later became galaxies, clusters, and the vast filaments that lace the cosmos. These fluctuations are mapped as differences of only tens of microkelvin, a whisper compared to the 2.725 Kelvin background. Their pattern is decomposed into angular scales, like musical notes, using multipoles that tell us how much structure appears at each size. The simplest models predict those fluctuations should be nearly Gaussian, meaning the statistics resemble a bell curve. In plain terms, most patches should be modest, and extreme hot or cold regions should be rare in a predictable way. When researchers claim an anomaly, they usually speak in sigma, and the language sounds like a courtroom. Sigma measures how far a result lies from expectation, given a model and its uncertainties, and it translates surprise into a number. 3 sigma is interesting. 5 sigma is treated as discovery, and both can mislead if handled carelessly. A posteriori choices, hidden systematics, and the temptation to tune a search after seeing the sky can inflate significance without changing reality. So we set rules before we chase dangerous ideas. Evidence must survive independent instruments, independent pipelines, and independent teams across time, because the universe does not care who wants a mystery. An anomaly must persist after foregrounds are removed, masks are applied, and null tests are passed. It must not vanish when the analysis choices change, and it must not depend on one clever trick that only works once. And even then, an anomaly has 3 mundane exits, which is why cosmologists sound cautious on camera. It can be a measurement artifact, a rare statistical fluke, or a clue to new physics that forces a rewrite. NASA and ESA built the tools to test that difference, and they did it with engineering that borders on obsession. WSMAP and Planck were designed to turn microwave noise into a calibrated map of the sky, where every pixel comes with an error budget. They do it by scanning the whole sphere repeatedly, measuring intensity differences with exquisitely stable detectors that must not drift. The spacecraft spin, precess, and trace interlocking circles, building redundancy so that one bad pass cannot dominate the story. They observe in multiple frequency bands because the sky is not only the CMB, different sources brighten or fade with frequency, so a true cosmic signal can be separated from imposters by its spectrum, like identifying instruments by their timbre. The Milky Way is the first obstacle, and it is not a small one when you look in microwaves. Dust emits thermally, electrons radiate synchrotron as they spiral in magnetic fields, and ionized gas produces free emission that can mimic cosmic structure. Even beyond our galaxy, there are point sources and faint backgrounds that complicate the picture. Radio galaxies, quasars, and clusters can add their own signatures, and each must be modelled or masked without carving away the cosmic truth. Data cleaning subtracts those foregrounds using templates and spectral behaviour, and it is both science and judgment. It also introduces controversy, because subtraction can remove truth or create patterns, especially when the signal we want is weaker than the contaminants. Analysts apply masks to cut out the brightest galactic regions, leaving a cleaner but incomplete sky. They test alternative masks, alternative component separation methods, and alternative calibration assumptions, because a robust result should not depend on one aesthetic choice. The goal is not a pretty picture, even though the maps are hypnotic and famous. The goal is a statistical sky that can be compared to LCDM, pixel by pixel, and multipole by multipole, with uncertainties that can survive skepticism. In that cleaned sky, one feature keeps returning, like a stain that reappears after every careful wash. It is a region colder than expected, larger than expected, and stubbornly difficult to dismiss, even when we try to treat it as ordinary. It is called the CMB cold spot, and it sits near the constellation Eridanus, away from the galactic plane where foregrounds are worst. On visualizations, it looks like a blue depression in a mottled field, a dip that draws the eye even when you resist. Its angular scale is several degrees across, depending on how you define its boundary and what filter you apply. That means it spans a patch of sky many times wider than the full moon, large enough to feel like a feature rather than a fluctuation. Its temperature decrement is on the order of tens to over 100 microkelvin, depending on the statistic used. In absolute terms, that is tiny, yet in relative terms, it is a conspicuous departure from what a Gaussian sky usually offers at that size. What drew attention was not just that it was cold, because cold patches exist everywhere in a random field. It was that its profile looked unusual, and some tests suggested non-Gaussian behavior, as if the cold region had an organized shape. Non-Gaussian means the statistics of the fluctuations might not be purely random, at least not in the simplest sense. It hints that the early universe may have been shaped by something structured, or that our assumptions about randomness are incomplete. But hints are not verdicts, and the cold spot sits at the edge of what chance can produce in a sky this large. The question is whether it is improbable or merely memorable, a coincidence that becomes famous because it has a name. Map saw it first, and Planck saw it again with different hardware and different systematics, which is why the bruise metaphor refuses to die. When two missions agree, the mind wants to promote the feature from artifact to event. Still, repeatability does not guarantee cosmic origin, and that is where the paranoia becomes useful. Both missions look through the same galaxy, and both rely on models to remove what the galaxy adds, so shared assumptions can create shared illusions. So the investigation begins with humility, and with suspicion aimed at our own tools. We treat every pipeline step as a potential source of self-deception, because the most dangerous ideas often arrive wearing the mask of a processing choice. We also treat the cold spot as a narrative test, not just a statistical one. If it is real, it challenges the smoothness we assume, and it forces us to ask why the universe would mark one direction with an outsized feature. One explanation stays inside our universe, and it begins with gravity and the slow passage of light. A giant underdensity along the line of sight could make CMB photons lose less energy climbing out of gravity wells, leaving them slightly cooler when they reach us. That mechanism is the integrated Sachs, Wolf effect to the ISW, and it depends on cosmic acceleration. In an accelerating universe, gravitational potentials decay with time, so photons can gain or lose net energy as they traverse evolving large-scale structure. If Eridanus contains a supervoid, it could imprint a cold region by the ISW, adding a secondary anisotropy on top of the primordial pattern. Surveys have searched for such a void using galaxy counts and redshift maps, and the results remain debated. Some studies report an underdensity, but not deep enough or wide enough to explain the full temperature drop implied by the cold spot. Others argue the void statistics are sensitive to selection and method, and that different tracers can paint different depths. There is also a subtle conceptual tension in the void idea. Even when a void is real, the ISW signal from a typical void is usually modest, so explaining a dramatic cold region may require an unusually large, unusually aligned structure, which itself becomes a probability question. Another explanation stays inside the data, and it is the one that makes statisticians shrug. The cold spot could be a statistical fluke, the kind that appears somewhere when you search a sky with millions of pixels and many ways to define unusual. That is the look elsewhere problem, and it haunts every claim that begins with a map and ends with a headline. If you define the anomaly after you see it, you bias the probability in your favour, even if you never intend to. A third explanation is the one we will not rush to, but we will not censor, because mystery is part of honest science. The cold spot could be a scar from beyond our cosmic horizon, an imprint left by an event that happened outside our observable patch. In some models of eternal inflation, bubble universes nucleate and expand within a larger inflating space. Collisions between bubbles could leave circular or localized imprints in the CMB, not as cartoon rings, but as subtle distortions in temperature and polarization. Those imprints are predicted to be faint, and the searches are difficult because we only have one sky to examine. But the cold spot has been discussed as a candidate signature of collision, partly because its scale and profile invite that kind of interpretation. Collision is only one version of the larger idea, and the larger idea is the one that unsettles people. Leakage suggests interaction across boundaries, perhaps through higher dimensions or neighbouring regions of reality, where outside is not a place in space, but a condition of the cosmos. If that sounds like science fiction, remember the standard model of cosmology was once a dangerous idea too. It became facts about space because it made testable predictions, and because those predictions survived instruments that were built to prove them wrong. Our job is to separate mystery from mirage without killing curiosity, and that balance is harder than it sounds. We follow the evidence, and we keep track of what each hypothesis must explain, including what it must not accidentally predict. To do that, we build a season-long mystery board, and we pin each clue with its own uncertainties. The cold spot is one pin, but it is not the only tension in the map, and it may not even be the most informative. There is the Eridanus Supervoid question, and the ISW effect question, and whether large-scale structure can really account for what we see. Those threads stay local, grounded in surveys, selection functions, and the slow architecture of matter. Then there are threads that feel larger than local because they flirt with preferred directions and coherent motion. Reports of dark flow suggested galaxy clusters might share a bulk motion, as if pulled by something beyond the horizon, although the measurements and interpretations remain contested. Dark flow remains disputed, but it points to a theme that keeps returning in different guises. The universe may have preferred directions that the cosmological principle says should not matter, and the question is whether those directions are physical or procedural. Closer to home, the Great Attractor is a gravitational region influencing local galaxy motions, inferred from peculiar velocities rather than direct brightness. It is partly explained by visible mass, but historically it felt like a hidden hand, because it was first seen as motion before it was seen as structure. Newer reconstructions describe a dipole repeller and other features in the cosmic velocity field. Mapping pushes and pulls across enormous distances, they translate motion into a kind of topography, where basins attract and ridges repel, and the resulting picture can look like intent. Most of these effects have conventional explanations in large-scale structure, and many fade as data improves. But together they form a question about scale, alignment, and whether our cosmic neighbourhood is typical, or whether we are sitting in an unusual patch of the universe. This documentary does not assume a parallel universe is real, and it does not promise a NASA discovery on demand. It asks whether multiple independent anomalies point in the same direction, or merely rhyme by coincidence, the way patterns emerge in clouds. We will treat each claim as a case file, and we will keep the paperwork visible. What instruments saw it? What frequency bands confirm it? What foreground model subtracts it? And what statistics survive it when the easy choices are replaced with hard ones? We will also ask what would count as a NASA discovery in this domain, where certainty is expensive and the sample size is one. Not a headline, but a result that persists across missions, methods, and years, even as teams try to break it. The stakes are not academic, because assumptions become levers that move everything else we infer. If the cosmological principle fails, then the scaffolding of LCDM must be revised, and our inferences about time and origin shift in ways that ripple across astronomy. If inflation's simplest predictions fail, then the early universe may have had structure we do not understand, and the smooth beginning becomes a story we told ourselves. If the CMB contains scars, then the cosmos has a history of contact, and contact implies an environment, and if contact is possible, then physics is not closed in the way we casually assume. The dangerous idea is that our universe is not a sealed system, and that boundaries can be crossed, leaving signatures small enough to hide in microwave static. That is where existential dread enters, not through monsters, but through measurement and calibration. A few microkelvin could imply that reality is porous, and that the calm we project onto space is a product of distance, not of truth. Humans have always mapped the unknown because maps turn fear into questions, and questions can be tested. The CMB is a map of the earliest accessible time, and it is written in microwave static that becomes meaningful only when we learn how to read it. Voyager 2 crossed the outer planets and kept going, leaving the solar system behind with a quiet stubbornness. It carried our instinct to explore into interstellar space, where the sun becomes one star and the familiar becomes a coordinate. WMAP and Planck did something similar in a different direction, and their journey is easy to underestimate because it is not measured in kilometers. They traveled not outward, but backward, using faint radiation to reach the edge of our observable universe and the limit of direct evidence. That is the paradox of this mystery, and it is why the cold spot matters even if it is mundane. The most terrifying thing in space might not be a black hole, but a bruise in the sky that suggests the universe has a story we have not heard. If the bruise is real, it is evidence that something happened to the early universe and that the event left a coherent trace. If it is not, it is evidence that our methods can fool us and that the human hunger for pattern can outpace the data. Either way, the investigation matters because it tests how we know what we know and how easily we confuse signal with story. It tests whether astronomy can distinguish a genuine anomaly from the seductive artifacts of cleaning, masking, and interpretation. So we begin with the baby photo, and we zoom in until the smoothness breaks and the grain becomes a landscape. We ask why one region is colder and what it demands of the cosmos, and whether the demand is physical or psychological. Next, we follow the most conservative lead first. We go to Eridanus, we trace the Supervoid claim, and we measure how much cold a void can truly make, given what LCDM already allows. From there, we widen the board to flows, alignments, and beyond horizon pulls, and we watch for the same signature in different places. If another reality is leaking into ours, it should leave more than one bruise, unless we have misunderstood what a bruise is. Next, we follow the most conservative lead first. If the cold spot is not a scar from outside, it should have a local cause. Cosmologists start with structure we already know exists, because the universe is lumpy even in LCDM. The letters are shorthand for a specific recipe: cold dark matter plus a cosmological constant. And that recipe predicts statistical roughness, not perfect smoothness. On the larger scales, galaxies trace a cosmic web that looks almost biological in motionless light. Filaments connect clusters like glowing tendons, sheets bridge gaps like faint curtains, and voids open between them like dark basins. In a wide-field visualization, the bright knots of clusters feel crowded, while the spaces between them feel unnervingly quiet. A cosmic void is not empty space, and that distinction matters for the story. It is an underdensity, a region where the matter density falls below the cosmic mean, not a region where physics stops. The void still contains dark matter, thin gas, and occasional galaxies, just fewer of them spread farther apart. In simulations, voids are expected because gravity amplifies contrasts over time, and it does so relentlessly. Dense regions pull in more matter, which deepens their gravitational potential and accelerates growth. Emptier regions lose matter to their surroundings, which makes them emptier still, an evacuation driven by the same gravitational bookkeeping. This picture has a history, and it's not new to the era of precision satellites. In the late 20th century, redshift surveys began to reveal enormous empty-looking regions, and the discovery of the Butter's void helped make void a mainstream term. Those early maps were sparse, yet they hinted at a universe organized by absence as much as by presence. LCDM does not just predict that voids exist, it predicts a distribution of void sizes, shapes, and depths. Most voids are tens of megaparsecs across, often with irregular edges and substructure inside. They are not typically hundreds of megaparsecs wide, and they are rarely deep enough to be called extreme. So when anyone says supervoid, the claim is extraordinary by definition. It implies an object in the extreme tail of the standard distribution, where statistics get thin and cosmic luck starts to dominate. It is not impossible, but it is the kind of thing you expect to see rarely in one observable volume. The proposed culprit sits in the same direction as the cold spot near Eridanus, and that alignment is why it became famous. It is described as a vast underdensity along our line of sight, as though a tunnel of reduced matter runs through the web. In sky maps, the cold spot is a clear depression, and the supervoid is the tempting shadow behind it. If that underdensity is real, it could affect the CMB without touching the early universe. It would act later, after recombination, as the photons travel for billions of years. That timing is crucial, because it keeps the explanation inside known cosmic evolution rather than exotic beginnings. The mechanism is the integrated Sachs, Wolf effect, usually shortened to ISW. It is a secondary imprint added after recombination, not a primordial fluctuation frozen into the plasma. In other words, it is a late-time edit, subtle but physically motivated, written onto an ancient photograph. The accessible version is simple, and it begins with gravity as geometry. CMB photons fall into gravitational wells and climb back out, trading energy with space-time curvature as they pass. The photon's wavelength stretches and compresses slightly, and we read that shift as temperature. In a universe with only matter, the wells stay steady while photons pass through them. The energy lost falling in is regained climbing out, so the net change cancels. That cancellation is why the original Sachs, Wolf effect, is tied to the early universe, where potentials were effectively fixed on large scales. But dark energy changes the timing, and timing is everything for ISW. In an accelerating universe, large-scale gravitational potentials decay as the photon crosses, because the growth of structure slows relative to the expansion. The well becomes shallower during the transit, an evolving landscape rather than a static valley. When a potential decays, the in and out legs do not cancel perfectly. The photon can leave with a net shift in energy, because it climbs out of a shallower well than the one it fell into. That shift is tiny in absolute terms, yet it becomes visible when averaged over large angular scales. For overdensities, the ISW tends to create slightly hotter patches, because the decaying well gives the photon a small boost. For underdensities, it tends to create slightly colder patches, because the potential hill also evolves, and the photon loses a little more than it gains. The sign depends on the geometry of the potential and its time evolution, not on any special property of the photon. In visuals, you can imagine a marble rolling through a dip in a rubber sheet, except the sheet relaxes while the marble moves. The marble's speed changes, not because the marble is special, but because the surface itself is changing. That is the ISW idea in plain language. Space-time shifts while the light is inside it. That is the mainstream pitch, and it is not a fringe idea. A big void could imprint a cold region, and the cold spot could be partly explained without rewriting cosmology. The appeal is psychological as well as scientific, because it keeps the anomaly inside the known cosmic web. The tension begins when we ask for numbers, not narratives. How cold can a realistic void make the CMB at the right scale? The cold spot is large in angle and deep in temperature, and it also has a profile that looks coherent rather than noisy. Depending on statistic and filter, the decrement can approach tens of microkelvin, which is not trivial against a background of random fluctuations. Typical ISW signals from typical voids are smaller, and that is where the discomfort starts to grow. Many analyses expect only a few microkelvin for common void parameters, especially when realistic density profiles and survey-based depths are used. The ISW is real, but it is usually gentle. To reach the observed amplitude, the void must be unusually large, unusually deep, or unusually well placed in redshift. Often it must be all three, and it must also be shaped in a way that concentrates the effect. Each requirement has a physical reason, and each one narrows the odds. Size matters because the ISW integrates along the path, and the photon's path is long. A longer traversal through an evolving potential yields a larger net effect, because the photon spends more time in the changing geometry. In a schematic, the area under the curve grows with distance through the structure. Depth matters because the gravitational potential difference sets the scale of the energy exchange. A shallow underdensity barely perturbs the photon's energy budget, even if it is wide. A deep underdensity changes the potential more strongly, but deep voids are statistically rarer in LCDM. Redshift matters because dark energy dominance is late, and ISW is strongest when acceleration is significant. In the deep matter era, potentials are closer to constant, so the cancellation returns. A void at just the right cosmic time has more leverage than a void that is too early or too late. And alignment matters because the cold spot is localized, not a global pattern. The void must sit almost exactly on the same line of sight, so the imprint lands where the temperature map is already depressed. A near miss does not create a near match, because the angular profile is part of the anomaly. Each requirement is plausible alone, and that is why the hypothesis stays alive. The problem is the conjunction, because LCDM already budgets how often extremes occur in one sky. When you stack improbabilities, you do not just add them, you multiply them, and the product can become uncomfortably small. This is where the term improbable explanation earns its weight. The void hypothesis can fit, but it strains the typical parameter space, and it asks the universe for a very specific arrangement. The story remains conservative, yet it begins to feel tuned, an ordinary mechanism forced into an extraordinary pose. Researchers try to test the claim with galaxy surveys, because galaxies are the practical traces we can count. If a supervoid exists, there should be a deficit of galaxies across distance, not just a dip on the sky. The logic is straightforward. Fewer galaxies implies less matter, and less matter implies a weaker gravitational potential. They use redshift mapping to turn positions into a three-dimensional picture, and this is where the work becomes technical. Redshift is a proxy for distance through Hubble expansion, but it's also perturbed by peculiar velocities. The method relies on selection functions and completeness, because every survey has a limit where it stops seeing faint objects. Some surveys reported an underdensity in that direction, and those results fueled the supervoid narrative. The feature looked extended, and it appeared to span a broad redshift range, which made it sound like a single vast structure. In an animation, you can watch galaxy density thin out like fog lifting, leaving a corridor of relative emptiness. Other teams found a weaker deficit, or a structure broken into smaller voids. The result depends on tracer choice and void finding algorithm, because void is not a single definition. Some algorithms search for spherical underdensities, while others allow complex shapes that better match the web. A key complication is that galaxies are biased tracers of mass, and bias is not a footnote. A galaxy underdensity does not translate one-to-one into matter underdensity, because galaxies form preferentially in denser regions. In a void, the dark matter may be low, but the galaxy count can be even lower, an amplified emptiness that exaggerates the visual impression. Bias depends on galaxy type, luminosity cuts, and redshift, and those choices can quietly steer conclusions. A survey can exaggerate emptiness if it preferentially misses faint galaxies, or if it selects luminous red galaxies that avoid low-density environments. The map you build is partly a map of your selection strategy. Survey depth sets the horizon of the map, and that horizon can create false structure. If the catalogue thins with distance, a normal region can masquerade as a void because the survey simply stops seeing what is there. This is why completeness corrections are treated like infrastructure, not decoration. Photometric redshifts add another layer of blur, and blur changes geometry. Their uncertainties can smear structures along the line of sight, inflating apparent size and reducing apparent contrast. A narrow dip can become a broad trough when distance errors stack up. Masks and extinction matter too, even away from the galactic plane, because the sky is not uniformly transparent. Dust and star density can reduce galaxy counts in subtle patterns, and those patterns can correlate with survey strategy. In a visual overlay, the mask looks like a bite taken out of the data, an absence that can mimic the absence you are searching for. So the supervoid is not a single object you photograph, like a nebula with a clear edge. It is a statistical reconstruction from incomplete sampling of a complex web, and that reconstruction carries assumptions. The void is partly in the sky, and partly in the pipeline. Even if an underdensity is present, its geometry is debated, and geometry controls the ISW imprint. A long, shallow trough can look like one giant void in projection, especially when the tracer density is low. In 3 dimensions, it may be a sequence of underdensities separated by modest walls. Projection is the enemy of intuition, because the sky collapses depth into angle. A chain of moderate voids aligned by chance can mimic a single extreme structure, and the CMB does not tell you the difference. The photon integrates whatever it crosses, regardless of how we label it. Model dependence enters again when translating a void map into an ISW prediction, and this is where disagreements multiply. You must assume a density profile, often something like a compensated void with an underdense core and a surrounding ridge. You must also assume how that profile evolves with time as structure grows and dark energy dominates. You must also assume how the potential decays in your cosmology, and small changes can matter. Adjust the matter density, the dark energy equation of state, or the growth rate, and the expected imprint shifts. The effect is subtle, but the cold spot is a subtle case built from subtle numbers. That uncertainty cuts both ways, and it keeps arguments alive. It can rescue the void explanation slightly, because error bars can be generous. It can also weaken claims of a clean match, because a flexible model can fit more than it should. The core dispute is simple to state, even if the calculations are not. The cold spot looks too strong and too coherent for the ISW from a typical void. The word typical is doing a lot of work because the whole debate is about tails. Some analyses conclude the void can explain only a fraction of the signal, perhaps a modest contribution. The rest must be primordial, or something else entirely, because the temperature decrement is too deep. In that view, the void is not the cause, it is an accessory. Others argue the statistics of voids in our one observable volume allow rare extremes, and they treat the cold spot as that rare case. They point out that improbable is not the same as impossible, especially when the sky offers billions of independent lines of sight. The universe, after all, gets many draws. But rarity is not free, and this is where the accounting becomes philosophical. If you invoke a rare void to explain a rare CMB feature, you must account for the combined odds, not just each oddity in isolation. Otherwise you risk turning coincidence into a narrative engine. That brings us back to the rules before dangerous ideas, because anomalies are fragile objects. We have to ask how the anomaly was found, and how significance was computed, because discovery methods shape what looks surprising. A feature can feel shocking simply because we searched in a way that guaranteed a shock somewhere. The look elsewhere effect is not a technicality, it is a warning label. If you scan the sky with many filters, across many angular scales, one region will look exceptional. The human eye is also a filter, and it is very good at finding faces in noise. A posteriori selection is the quieter trap, and it is more common than anyone likes to admit. If you define your test after seeing the cold spot, you bake surprise into the metric because the metric is tailored to what you already noticed. The result can be a significance that measures your curiosity as much as the cosmos. When teams correct for those choices, the cold spot's significance often shrinks, sometimes dramatically. It can drift from dramatic to merely uncommon, which changes the emotional temperature of the debate. The spot remains real in the map, yet its demand for new physics becomes less urgent. That does not erase the feature, and it does not erase the discomfort. It changes what it demands from theory, and it changes how much weight we place on coincidence. In a space documentary, this is where the narration slows down, because the difference between weird and impossible is where good science lives. The void claim faces the same statistical accounting, and it must survive the same discipline. If you searched many directions for underdensities, one will align with something interesting, because the sky is full of structure. The question becomes whether Eridanus is special in an objective way, or special because we pointed at it first. Planck and WMAP complicate the easy dismissal, and they do so in a way that feels stubborn. The cold spot persists across instruments, scanning strategies, and independent pipelines, and it persists across years of scrutiny. That persistence argues against a simple detector glitch, which is why the story does not end quickly. It does not eliminate subtler systematics that can survive multiple missions, and that is the uncomfortable middle ground. Two experiments can share assumptions, share foreground models, and share the same sky. A systematic that is astrophysical rather than instrumental can also persist, because it is truly in the data. So we interrogate mundane culprits with the same discipline, and we do it in public. Foregrounds, beams, and map-making can all sculpt false structure, especially on large angular scales where calibration matters. The cold spot is a test case for the entire chain from raw voltages to cosmological interpretation. Residual foregrounds are the first suspect, because the Milky Way is bright and complicated. Galactic dust emits thermally, synchrotron radiation traces magnetic fields, and free emission follows ionized gas. Each component has its own spectrum and spatial texture, and those textures can masquerade as cosmological features if subtraction is imperfect. Planck cross-checks frequencies because the CMB has a near-perfect blackbody spectrum, and that is a powerful constraint. Foregrounds change with frequency, so mismatches reveal contamination, at least in principle. In frequency maps, a true CMB feature should keep the same temperature contrast after proper conversion, while foregrounds should not. Component separation methods also differ, and that difference is a strength. If a feature survives SMICA, NILC, CVM, and Commander, confidence increases because those methods make different assumptions about foreground mixing. In a montage of maps, the cold spot sits there like a bruise that refuses to fade. Beam systematics are another suspect, and they are less intuitive but equally serious. Asymmetric beams can smear power in a direction-dependent way, and scanning patterns can imprint striping or localized artifacts. If a beam is slightly elliptical, the sky can inherit that ellipse in subtle ways. Map-making choices can leak large-scale modes into smaller scales, and calibration drifts can bias low multiples. Dipole subtraction errors matter because the dipole is huge compared to the anisotropies we care about. When you remove a signal thousands of times larger than the target, tiny mistakes can leave fingerprints. Planck runs null tests to hunt these issues, and those tests are part of the NASA-style discipline of space facts. They difference detectors, split data by time, and compare half-mission maps to see what cancels and what remains. A real sky feature should persist, while many systematics should not. The cold spot remains visible in cleaned maps, which is why it stays in the case file. Yet visibility is not the same as explanation, and that distinction keeps the chapter honest. A persistent feature can still be a statistical fluke, and a fluke can still be visually striking. If the void cannot fully account for the amplitude, the mainstream story becomes a hybrid. Part primordial fluctuation, part late-time ISW, stitched together into a single observed depression. A hybrid reduces the burden on the void because it no longer has to do all the work. It also reduces the satisfaction because it turns the explanation into bookkeeping. Bookkeeping can be correct, and it can be the best answer available, yet it rarely feels like closure. The cold spot in this framing becomes an unlucky overlap of two ordinary effects, and bookkeeping does not answer the eerie part, which is emotional but also statistical. Why does a debated supervoid sit so neatly behind a rare CMB depression, as though the universe arranged a demonstration? Even careful scientists feel the tug of that question, because alignment is a pattern our brains are built to notice. Alignment is the chapter's pressure point, and it is where the tone turns mysterious without turning careless. In a statistically isotropic universe, alignments occur, but they should not feel scripted. When a feature looks staged, the first task is to prove that the stage is not an illusion. If the void is real, it becomes another improbable coincidence stacked onto the cold spot. The void stops being a solution and becomes a clue, because it suggests the line of sight might be special. The cosmos is not supposed to privilege one direction, and yet here we are staring down a particular corridor. Space facts can be comforting when they are ordinary, because they make the universe feel lawful. Here, ordinary physics produces a pattern that still feels strange, and that is the unsettling twist. The same equations that explain most of the sky leave one patch that keeps resisting easy normality. NASA does not announce parallel universes from a cold patch, and that restraint is part of the culture. NASA builds instruments that force our stories to survive cross-examination, and it funds analyses that try to kill exciting ideas. In this sense, skepticism is not cynicism, it is quality control. So we keep the conservative frame while admitting the discomfort. The Eridana supervoid is plausible, but it is not comfortably sufficient, at least not in the most straightforward models. The void can contribute, and it can even be large, yet the amplitude problem keeps returning like a refrain. At this point, the documentary has to widen the hypothesis space without breaking method. We ask what else can make a spot, while keeping the burden of proof where it belongs. The goal is not to chase wonder, but to inventory explanations that do not collapse under known constraints. Some alternatives stay astrophysical, and they do not require new physics. A rare primordial fluctuation could produce a cold region with an unusual profile, because Gaussian random fields do allow tails. The question is whether the cold spot is merely a tail event, or a tail event with extra structure. Non-Gaussianity is one route, and it has a long history in CMB debates. If the primordial fluctuations deviate from perfect Gaussian statistics, you can get more extreme spots than expected. But non-Gaussianity is constrained by other CMB statistics, so any special mechanism must not ruin the rest of the sky. Topological defects have been proposed in the past, especially when cosmology was younger and the parameter space felt wider. Textures could create localized imprints by altering the gravitational field as they unwind, leaving hot or cold features. Current limits make them difficult, yet the idea remains part of the historical backdrop. Some alternatives stay systematic, and that is always worth revisiting because systematics are the most common cause of surprises. A subtle residual foreground could mimic a cold profile without obvious frequency dependence, especially if multiple components conspire. Even then, the burden is heavy, because the cold spot survives aggressive cleaning. Planck's polarization data becomes a judge here, because polarization carries additional information about origin. A primordial feature should correlate with polarization patterns in specific ways, because temperature and polarization are linked at last scattering. A late-time ISW feature, by contrast, has a weaker polarization counterpart. The cold spot's polarization tests are suggestive but not decisive, and that ambiguity matters. The data is noisy at the relevant scales and interpretation is delicate, especially with large angular features. In other words, polarization does not yet deliver a verdict that ends the trial, so the void remains the mainstream anchor, even as it wobbles under scrutiny. It is the least exotic story that can be told with known ingredients, and it respects the conservative instinct of cosmology. Yet the wobble is the point, because it signals that the explanation is not a clean closure. It does not restore the feeling of statistical normality, and that is why the chapter keeps its tension. The cold spot is not just cold, it is stubborn, and it keeps making ordinary explanations feel slightly incomplete. The cosmos offers a feature, then withholds the simple reason. This is where cosmic horror enters through arithmetic, not through imagery. The universe does not need monsters when probability itself can generate dread. If the cold spot were only a void imprint, the case would end with large-scale structure, and the mood would settle. Instead, the numbers keep leaving residue, and residue is what scientists learn to respect. That residue invites a careful, quarantined speculation, one that is acknowledged without being embraced. Some inflationary models predict bubble collisions that leave circular or spot-like signatures, and that prediction is part of the literature. Eternal inflation is not a ghost story, even if it sounds like one in a late-night narration. It is a theoretical framework where inflation continues elsewhere, producing many pocket universes with potentially different conditions. The idea arises from how inflation can be self-reproducing in certain potentials, and it is debated because it pushes against testability. If bubbles collide, the boundary can perturb the inflaton field and the metric, and that perturbation can propagate into observable signatures. The result can be a localized temperature modulation, sometimes described with disk-like profiles. In principle, it could also leave polarization patterns that differ from ordinary fluctuations. Searchers look for disks, rings, and specific profiles in temperature and polarization, and they do so with template matching. The evidence is not conclusive, but the templates exist, and the methods are published. This is not a claim of discovery, it is an example of how theory tries to make itself falsifiable. We do not claim the cold spot is a collision, and we keep that line bright. We note that the shape and isolation keep it on the list of candidates, because it is an outlier that invites structured explanations. The parallel universe narrative must be seeded with restraint, or it becomes a story that eats the data. Extraordinary claims require multiple independent signatures, not one famous patch. They require consistency across temperature, polarization, and large-scale structure, and they require predictions that survive new data. A single anomaly can be the first clue, but it can also be the last coincidence. Still, the alignment question refuses to stay quiet, because it sits at the intersection of objects, time, and geometry. A void aligned with a rare CMB feature can be coincidence, or it can be fingerprint, and the difference is not rhetorical. The difference is whether the universe is merely random, or subtly connected across epochs. A fingerprint is not proof of intent, and it is not proof of anything supernatural. It is a pattern that repeats across different evidence streams, in objects, time, and scale, and it resists being averaged away. The cold spot has not yet earned that status, but it keeps asking for the test. So we end this chapter with the conservative explanation intact but weakened, which is an honest place to stand. The Eridanus supervoid may exist, yet it does not end the story, because it does not fully pay the temperature bill. It changes the story's shape because the void becomes part of the evidence that our universe may not be a sealed container. If another reality is leaking into ours, it might not announce itself with fireworks. It might hide behind plausible structure, then overperform, leaving just enough mismatch to keep the mind awake. And that is the terrifying spread, because each attempt to explain the cold spot locally leaves a small remainder that points outward. In the next chapter, we follow that pointing, and we do it with the same rules in hand. We move from one anomaly to patterns of direction, motion, and the possibility of a larger contact. So we set rules before we chase dangerous ideas. Then we chase them anyway, because method is how fear becomes astronomy facts. So we set rules before we chase dangerous ideas because the universe rewards curiosity only when it is disciplined. The Cold Spot asked whether the early universe carries a scar, a bruise in temperature that should not be there. Now we ask whether the cosmos is also moving oddly, and whether the motion itself hints at something unseen. Expansion is the baseline story, and it is easy to misunderstand when the visuals look like an explosion. In the simplest picture, galaxies are not flying through space like shrapnel, because there is no central blast site. Space itself stretches, and the distance between widely separated galaxies grows with time, even when neither galaxy fires an engine. That relationship is the Hubble flow, and it can be written as a clean proportionality. Recession speed increases with distance. On screen, this is the moment for a calm geometric animation, because calm is the corrective to intuition. A grid of space expands evenly, and every point recedes from every other point without any privileged center. The farther a galaxy sits on that grid, the faster the grid carries it away on average, and that average is the key word. The universe is statistical. Real galaxies live in a lumpy cosmos where local gravity bends the rule. Hubble's original discovery was not just a plot of redshift against distance, although that graph became an icon. It was a cultural shock because it turned the cosmos into a dynamical object with a history, and it made before and after scientific categories. Later, the interpretation became sharper through general relativity, where expansion is encoded in the metric that defines space-time intervals. The motion is not a force pushing galaxies outward, but a change in the scale that defines separation, and that distinction matters. But galaxies do not simply ride the expansion like leaves on a perfect river, because the river has whirlpools and shear. Gravity from nearby structure adds extra motion on top of expansion, and those deviations carry information about mass that may not shine. That extra motion is peculiar velocity, measured relative to the ideal Hubble flow, and it is not a rounding error. It is the difference between what the redshift suggests and what the distance actually is, once you correct for local motion. Peculiar velocity is not a technical footnote, because it is how we infer hidden mass without seeing it directly. If a galaxy is closer or farther than its redshift implies, something has tugged it, and the tug has a direction. Those tugs add up across clusters, filaments, and voids, creating a velocity field that traces the cosmic web like wind traces pressure. In the language of dynamics, velocity becomes a response function to the underlying gravitational landscape. In physical terms, peculiar velocities arise from gradients in the gravitational potential, which is the smooth field produced by all matter. Matter falls toward overdensities, and it streams away from underdensities, because the surrounding mass pulls harder than the empty center can resist. In linear theory, the velocity field is linked to the density field in a predictable way, with growth rates set by cosmological parameters. That is why velocities can become a kind of shadow map of mass, dark matter included. Visually, the web is a dark lattice with bright knots, and the camera glides along filaments like rails in a vast station. Arrows drift toward the knots, but they also peel away from the hollow regions, and the flow lines bend smoothly rather than jitter. The arrows are not random, they are coherent over tens of megaparsecs, because gravity integrates over large volumes and long times. The result is motion that feels like weather, except the atmosphere is made of galaxies and the storms take billions of years. We also have a more global reference frame, and it comes from the oldest light we can measure. The cosmic microwave background is nearly uniform, yet it has a dominant dipole pattern that overwhelms everything else in amplitude. One side is slightly hotter, the opposite slightly colder, and the axis is unmistakable across the whole sky. It is the loudest anisotropy in the microwave sky, and it is our first clue that rest can be defined cosmologically. That dipole is mostly Doppler shift from our motion relative to the CMB rest frame, and the physics is simple enough to trust. When we move toward the CMB, the photons appear slightly blue shifted, and the temperature looks higher by a few millikelvin. When we move away, the photons appear slightly redshifted, and the temperature looks lower by the same amount. It tells us the solar system is moving hundreds of kilometers per second, and it tells us in which direction. The number is not a vague impression, and it is not small by cosmological standards for a local observer. The measured dipole corresponds to a speed of about 370 km per second relative to the CMB frame, and the uncertainty is small. That value is a vector with a direction on the sky, and it becomes a cosmic compass for everything else. It also anchors a key fact about space, because motion becomes measurable against a standard that is not local. The dipole is huge compared to the microkelvin anisotropies we chase in chapters 1 and 2, and that scale contrast is a warning label. Those smaller patterns are the fossil ripples of early density fluctuations, and they are delicate, like texture on a nearly perfect sphere. Removing the dipole is essential, and errors can leak into large angular scales if the subtraction is imperfect. That is why every claim about preferred directions must survive brutal calibration and repeated null tests. On screen, the dipole removal is a surgical act, and the audience should feel the risk in the precision. A bright to dark gradient is stripped away, and the remaining map looks like mottled static with faint, coherent patches. The danger is subtle. If the instrument's gain drifts, or the beam is asymmetric, the subtraction can leave ghosts. Those ghosts can masquerade as deep cosmic alignments, especially at the largest scales where we have the fewest independent modes. Our motion is not just the Sun's orbit around the Milky Way, though that is part of the vector sum. The Sun circles the galactic center at roughly 220 km per second, and that motion has a direction tied to the plane of the disk. The Milky Way moves within the local group, then within the local sheet, then within the Laniakea region, and each layer adds a vector. Each addition is a piece of bookkeeping, and the sum becomes the dipole we observe. The hierarchy matters, because it turns a single number into a story of nested structures assembled over time. The local group is bound by gravity, with the Milky Way and Andromeda as its dominant masses, and their mutual approach is part of the local dance. The local sheet is a flattened arrangement of nearby galaxies, like a thin slab in the web, with coherent motion relative to surrounding voids. Laniakea is a larger basin of attraction, defined by the way galaxies stream through space toward a common region. This is where the story shifts from a bruise to a current. If gravity shapes the CMB through voids and potentials, gravity also shapes our trajectory through the web, and the trajectory becomes a diagnostic. The question is whether the trajectory is ordinary or too coherent for the scale we sample. Are we seeing the expected pull of nearby structure, or a drift that refuses to average out as we look farther? Darkflow entered the literature as a claim about bulk motion on enormous scales, and it arrived with the thrill of a possible crack in the cosmological principle. The idea was simple to state and hard to test, which is a dangerous combination in public science. Galaxy clusters spread across the sky seem to share a common drift, as if the universe had a preferred current. The phrase itself did narrative work before the data could finish the argument, and that asymmetry shaped the controversy. The method was not based on galaxy distances in the usual way, because distances are expensive and noisy at great range. It used the kinematic Sunyaev-Zeldovich effect, shortened to KSZ, which is a Doppler imprint on the CMB from moving cluster gas. It treats clusters as moving mirrors for CMB photons, though the mirror is made of hot plasma and the reflection is statistical. The effect is subtle, and that subtlety is the entire problem. In a cluster, hot electrons scatter CMB photons through inverse Compton processes, and the scattering probability is set by the electron column density. The thermal SZ effect changes the spectrum, revealing electron temperature and pressure, and it has a distinctive frequency dependence that multi-band experiments can separate. The KSZ effect is subtler because it depends on the cluster's line of sight velocity and produces a temperature shift with nearly the same blackbody shape. In practice, it hides in plain sight because it looks like ordinary CMB fluctuation unless you know where to look. To understand why, picture a photon C passing through a swarm of free electrons, with the cluster acting like a faint fog bank. If the electrons are at rest in the CMB frame, the scattering mostly redistributes directions, and the mean temperature stays the same. If the electrons have a bulk velocity, the scattered photons inherit a Doppler imprint, and the sign depends on whether the cluster approaches or recedes. The amplitude depends on the optical depth of the cluster gas, which is not directly visible and must be modelled. If a cluster moves toward us, scattered photons get a slight Doppler boost, and the CMB looks slightly hotter in that direction by microkelvin amounts. If it moves away, they get a slight decrement, and the difference is tiny compared to the CMB's own intrinsic modelling. In principle, a coherent bulk flow would imprint a coherent KSZ signal across many clusters aligned with a common axis. In practice, each cluster is a messy astrophysical object with its own complications and its own noise. The promise was seductive because it bypassed some distance ladder uncertainties, and it felt like a direct speedometer on the deep universe. You do not need standard candles for KSZ in the same way, and you do not need to measure individual galaxy distances inside the cluster. You need precise CMB maps, accurate cluster catalogues, and careful separation of tiny signals from larger ones. You also need the humility to assume the sky will try to trick you, because it will. The difficulty is that KSZ is small, often buried under primary CMB fluctuations that are larger on the same angular scales. It is also entangled with the thermal SZ signal, and with foregrounds from dust, radio galaxies, and our own Milky Way, which all add structure. You must model beams, noise, and selection effects with near-paranoid discipline, and you must verify that your filter does not manufacture a dipole. Even then, the result can hinge on one weighting choice that sounds innocent in a methods section. On screen, the KSZ signal is almost invisible, and that invisibility should be part of the visual language. The cluster positions are marked with circles, and the map looks like random mottling with no obvious pattern to the eye. Then the analysis stacks hundreds of clusters, averaging down unrelated CMB fluctuations and uncorrelated noise. The hope is that a coherent drift survives the averaging, like a faint tide revealed by long exposure and careful subtraction. Early analyses reported a bulk flow extending to scales that felt too large, and the language reflected the discomfort even as it courted attention. The claimed coherence reached hundreds of megaparsecs, sometimes approaching a gigaparsec, which is a meaningful fraction of the observable volume. In LCDM, large-scale flows exist because structure grew from tiny perturbations, but coherence should fade with scale. The largest modes have limited power, and randomness should wash out directionality as you average over more sky. If the flow persisted beyond the expected scale, the implication was unsettling, because it would not be a local fluke. It could suggest a gravitational pull from structures beyond the observable universe, a tide we cannot see directly but can feel through motion. It could also suggest primordial inhomogeneity that inflation did not erase, leaving a long wavelength gradient across our patch. Either way, it would mean the universe is not as statistically bland as we thought, and that typical might be a local illusion. The phrase dark flow was a narrative gift, because it implied an unseen current in the deep, and it sounded inevitable once spoken aloud. It sounded like a NASA discovery even when it was not one, and that distinction matters in public memory and in headlines. NASA discovery culture is built on careful language, because the cost of overclaiming is long-term distrust and long-term confusion. But the internet does not wait for error budgets, and the word flow carries its own momentum. The science lived or died on systematics, and systematics were everywhere, hiding in instruments and in assumptions. Other teams reanalyzed the same idea with different data and pipelines, often using different cluster samples and different filtering strategies. Some found the signal weakened or vanished under alternate choices, which is a red flag when the underlying physics should be stable. Some argued the detection was consistent with noise and residual CMB contamination, and the disagreement became methodological as much as empirical. A key problem is that clusters are not perfect test particles, and they are not identical spheres of gas. Their gas profiles vary, their optical depths vary, and their astrophysical environments add confusion that correlates with selection. Mergers can shock heat gas, feedback can reshape pressure profiles, and substructure can break spherical symmetry in ways that bias templates. If your assumed profile is wrong, your inferred velocity is biased, and the bias can align across a sample that was selected the same way. Another problem is that the primary CMB is itself structured on the same angular scales, and it does not politely step aside. If you stack clusters on a map, you can accidentally stack CMB features that have nothing to do with the clusters, especially if the cluster catalogue traces regions with particular sky properties. A coherent pattern can emerge from chance alignment and filtering artifacts, particularly when the statistic is tuned after looking at the data. The universe is not malicious, but statistics can be. Instrumental beams matter because they smear signals and couple modes that should be independent, turning a clean separation into a blended one. Scanning strategy matters because it can imprint subtle anisotropies, particularly when coverage is uneven and noise varies across the sky. Foreground cleaning matters because residual dust or radio sources can bias the stack, and the bias can mimic a dipole. Even the mask you choose around the galactic plane can shift the inferred dipole direction by a surprising amount. The conflict became a case study in how hard it is to measure motion in the deep cosmos, where signal-to-noise is a tyrant. KSZ is real, and it has been detected in other contexts, but extracting a bulk flow is a high-wire act over a canyon of systematics. The result depends on how you weight clusters, how you mask, and how you estimate covariance in the presence of correlated noise. When the signal-to-noise is low, methodology becomes destiny, and small choices become big outcomes. In the conservative reading, dark flow was not confirmed as a beyond-horizon tide, and that conservative reading gained strength over time. Later analyses with improved maps and catalogues did not reproduce a strong, coherent flow at the claimed amplitude, and some set upper limits instead. Planck's data, with different systematics than WMAP and different frequency coverage, became a critical cross-check. The controversy did not end the question, but it narrowed what could be true, and it raised the bar for any future claim. Still, the story does not collapse into nothing, because our local motion is undeniable and its causes must exist. We are moving relative to the CMB, and that motion must have causes in the mass distribution, including mass we do not see. The question becomes how much is explained by what we can map, and how much remains as an accounting problem. In cosmology, an accounting problem can become a doorway, because missing momentum points to missing information. This is where older names return because they were invented to explain motion before structure was mapped in detail. The Great Attractor was inferred from peculiar velocities of nearby galaxies, not from a single dramatic image or a single cluster. It was a gravitational region, not a single object, defined by convergence in the velocity field and by the way flow lines bent. The name was a placeholder for an influence, and placeholders can become myths if the data stay incomplete. In the late 20th century, surveys showed galaxies streaming in a general direction, and the stream was hard to ignore. The flow suggested a mass concentration pulling on the local group, and the inferred mass was enormous even by supercluster standards. Yet the sky in that direction is obscured by the Milky Way, where optical surveys struggle and confusion is high. The Great Attractor felt hidden because the evidence was kinematic rather than photographic, and because the map had a hole. That obscuration is the zone of avoidance, where dust and stars block optical surveys and confuse source identification in crowded fields. The Milky Way's disk is not just bright, it is structured, with extinction lanes and dense stellar fields that create false negatives and false positives. For decades, it cut a missing band through extragalactic maps, like a torn strip in a chart that refuses to be repaired. The Great Attractor lived behind that tear, and the tear shaped the story. It was a reminder that absence of light is not absence of mass, and that our catalogues are not the universe. Gravity does not care whether we can see the source, and peculiar velocities respond to total mass, including dark matter that never emits. That is why the Great Attractor story resonated with the dark matter era, when invisible mass became normal. It sounded like a hidden monster, but it was really a lesson in observational limits and inference. Infrared and radio surveys began to map through the dust, and the missing band slowly filled in with real galaxies. HI observations traced gas-rich galaxies through their 21 centimeter emission, which passes through dust more easily and provides clean redshifts. Near-infrared surveys traced older stellar populations, giving a different view of the same structures and reducing extinction bias. With each new catalogue, the hidden region became less blank, and the velocity story gained anchors. On screen, the zone of avoidance is first a dark stripe across a starfield, an absence that feels like censorship. Then the stripe becomes translucent as wavelengths change, and faint galaxies appear like embers behind smoke, arranged in filaments. The map gains continuity, and the flow vectors begin to make sense as they curve around real overdensities. The Great Attractor becomes less mystical, and more like a knot in the local web stitched into the same fabric. It sits in the direction of the Centaurus and Norma regions, associated with rich clusters and dense filaments that connect to broader structures. It is part of a larger gravitational landscape, rather than a lone monster, and that landscape has gradients rather than cliffs. In modern language, it is a region of overdensity embedded in a network of connected structures, with dark matter dominating the mass budget. The name remains, but the meaning becomes more precise, and precision is how myths die. But it was never the whole story, and that is where Shapley enters with heavier weight and farther reach. The Shapley supercluster is a massive concentration farther away, and it sits in roughly the same broad direction on the sky. Its mass and distance make it a major contributor to local flows, because gravity integrates over volume and coherent structure can dominate. Even fast structures can matter when they are enormous, and Shapley is enormous. Historically, Shapley's name carries a different echo, tied to early debates about the scale of the Milky Way and the nature of galaxies. Here, it returns in a new context, as a landmark in the large-scale structure era, where redshift surveys revealed superclusters as real entities. The Shapley concentration is not just a cluster, but a dense complex of clusters bound in a larger overdensity. It is a reminder that the cosmic web has hierarchy, and hierarchy drives motion across time. When you include Shapley and surrounding superclusters, more of our motion becomes explainable, and that is a sobering shift. Reconstruction suggests that a significant fraction of the local group velocity arises from known overdensities once you account for their mass and geometry. Yet the error bars remain, because mass mapping is incomplete, especially in regions of poor sky coverage and uncertain bias. The universe does not give us a full census, and it does not label its missing entries. Distance measurements are noisy, and peculiar velocity catalogues are sparse compared to redshift catalogues, which makes inference fragile. Methods like Tully, Fisher for spirals and the fundamental plane for ellipticals carry intrinsic scatter, and that scatter translates into velocity uncertainty. Malmquist bias and selection effects distort inferred flows, because brighter objects are overrepresented at larger distances and the sample is not uniform. Even the definition of the local rest frame can shift conclusions by tens of kilometers per second, which is enough to matter. This is why the narrative tension survives the collapse of a strong dark flow claim, because the underlying measurement problem remains. The cosmic velocity field is real, and it is complex, and it is sampled unevenly across the sky and across distance. It can look like a coherent stream when sampled poorly, then fragment under better data and better modelling. The question is not whether motion exists, but whether it contains an extra component that refuses to be filed away. Modern work reframes the question using velocity field reconstructions, which replace single monsters with maps. Instead of naming one attractor, researchers map basins and ridges in the flow, treating the local universe like a landscape with slopes. They use galaxy surveys and linear theory to infer the gravitational potential field, and they propagate uncertainties carefully. From that potential, they derive expected velocities and compare them to observations, looking for residuals that might signal missing structure. In that landscape, attraction is only half the story, and the other half is emptiness with consequences. Underdense regions also shape motion, because matter flows out of voids as structure grows and as surrounding overdensities pull more strongly. A void can act like a repeller in the velocity field, even though it is not a force source and it contains no engine. The repeller is a geometric description of flow divergence, not a new kind of gravity, and the distinction keeps the physics honest. This leads to the dipole repeller concept, a counterpart to the attractor narrative that changes the emotional framing. Our motion can be described as being pulled toward overdensities and pushed away from a large underdensity, and the vector sum can match the observed dipole direction. The void becomes an active presence in the map of motion, because the surrounding mass pulls matter outward and away. The name is provocative, but the mathematics is ordinary, and ordinary mathematics can still describe strange outcomes. Calling it a repeller risks anthropomorphism, so we keep the physics clean and the language restrained. Gravity pulls, and expansion plus gradients move matter from high to low density in a way that can be derived from the continuity equation. In the reconstructed flow, the vector field points away from voids because there is less mass to hold matter in, and the surrounding mass wins. The repeller is the place where the flow lines seem to originate, like streamlines rising from a valley in reverse. Yet the psychological effect is powerful, because it makes absence feel dangerous, and it makes emptiness feel like agency. A repeller suggests the universe can steer us with nothing, using a deficit as a sculpting tool for trajectories. It echoes the cold spot logic, where a void might imprint a cold scar by evolving potentials along the line of sight. In both cases, the void is not a blank but an actor, and the actor is defined by what is missing. Now, the documentary board has 2 pins that rhyme, and the rhyme is structural rather than poetic. One pin is a cold region that may be partly explained by an underdensity along the line of sight, a void that changes photon energies subtly. Another pin is a motion field where underdensity shapes our trajectory, bending flow lines across the local universe. The question is whether these rhymes are ordinary consequences of large-scale structure, or hints of something deeper that we have not named. LCDM predicts a web with voids and clusters, and it predicts flows driven by that web through gravitational instability. It also predicts statistical variance that can produce unusual alignments in one realization of the sky. Because we only get one sky, we only get one universe to observe, and cosmic variance is the price of that uniqueness, paid in uncertainty at large scales. The model expects some oddities, but not unlimited ones, and the boundary matters. But LCDM also predicts a scale beyond which bulk flows should average out because the universe becomes homogeneous in the mean. As you consider larger and larger volumes, random directions cancel, and the net drift diminishes, leaving only small residuals. If a coherent flow persisted on scales too large, it would demand explanation, and it would demand it loudly. That is where the phrase "beyond the horizon" becomes more than poetry, because it becomes a hypothesis with testable consequences. If something outside our observable universe exerts gravitational influence, it would not send light we can see, because its light has not had time to reach us. It would only tug through the metric, shaping motion, and perhaps shaping the largest CMB modes that are sensitive to long wavelengths. The idea is not forbidden by relativity, but it is constrained by consistency across datasets. A strong tide would also distort the CMB in ways we can test, and that is the trapdoor such ideas must step over. One conservative possibility is primordial inhomogeneity within our own inflationary patch, a leftover gradient that never fully smoothed. Inflation may not have smoothed everything perfectly if it was short, or if it began in an unusual state that biased the largest modes. A long wavelength mode could tilt our region, creating a preferred direction in density and velocity that looks like a cosmic breeze. In plain terms, our patch could be slightly tilted, and we would live inside the tilt. Another possibility is anisotropic inflation, or a pre-inflationary relic, where initial conditions leave a gradient that survives as a superhorizon perturbation. In some models, the early field dynamics allow a small directional dependence that imprints correlations between the CMB and matter distribution. That gradient could tilt the CMB and the matter distribution together, producing correlated anomalies that rhyme across chapters. The challenge is to do this without ruining the near isotropy that the CMB so strongly displays, because the CMB is a strict judge. A more speculative possibility is an external gravitational tide from beyond our horizon, an influence that is real but causally distant. In eternal inflation pictures, neighbouring bubble universes could create a large-scale potential gradient, and even without collision, their presence could bias our local expansion and flows. The hypothesis is dramatic and it is easy to narrate, which makes it dangerous. The evidence must be equally strong, and it must survive the next generation of instruments. We do not treat that as a conclusion, because the evidence is not clean, and the systematics are too cunning. We treat it as a hypothesis that must earn its keep across multiple datasets, with predictions that survive new instruments and independent pipelines. It must explain why the CMB is nearly isotropic while still allowing a large coherent motion, and it must do so quantitatively. It must also avoid becoming a story that explains everything, because that explains nothing, and it dissolves into unfalsifiability. This is where measurement difficulty becomes part of the horror, because it limits closure and invites doubt. KSZ is tiny, peculiar velocities are noisy, and the sky gives us one realization with one set of foregrounds and one galactic plane. The universe can hide a real effect inside error bars for decades, and it can also manufacture a false effect from subtle systematics. Which is more frightening, a hidden tide, or our inability to know which tide is real? NASA discovery culture is built to resist that uncertainty by demanding redundancy and falsification, not just excitement. Planck, WMAP, and ground-based CMB experiments provide cross-checks with different detectors, different scan strategies, and different frequency coverage. Large galaxy surveys provide independent mass maps, and each new catalogue tightens the net around what is plausible. The goal is not a single dramatic detection, but convergence, agreement that survives method changes. Yet the net is still incomplete beyond certain distances, especially near the zone of avoidance where the Milky Way still interferes. dust still blocks, and selection still bites, and the far web is still undercounted, especially for faint galaxies and low surface brightness structures. Even outside the plane, survey depth varies, and completeness is never perfect across the whole sky. The Great Attractor story reminds us that unseen does not mean non-existent, and that missing data can mimic missing physics. To keep scale in mind, we anchor the human contrast with machines that feel far away, because scale is where intuition fails. Voyager and Voyager 2 drift through interstellar space after decades of travel, their power dwindling and their signals thinning into the noise. Their distance is enormous to us, measured in light hours and astronomical units, and it feels like the edge of reach. Yet it is microscopic compared to megaparsec flows, where entire clusters drift as if on slow currents. A megaparsec is 1,000,000 parsecs, and a parsec is already a unit built for stars rather than people. 1 parsec is about 3.26 light-years, a distance that dwarfs the solar system and makes Voyager look like a local errand. Clusters move through tens and hundreds of megaparsecs as structure grows, guided by gravity over deep time and deep volume. Our entire solar system is a speck riding a gravitational current, and the current does not notice us. The terrifying spread in this chapter is not a monster, but a possibility with consequences that scale upward. If large-scale motion contains a coherent component that should not exist, then the anomaly is not localized like the cold spot, and it is not easily quarantined. It would be a directional feature written into the dynamics of the cosmos, not just into its temperature map. It would mean the universe is not only marked in temperature, it is also being steered, and steering implies an environment. A bruise is a trace of contact, but a flow is ongoing contact, and that difference changes the stakes. The difference is between an ancient scar and a present pull, between a fossil and a force that continues to act. If the current is real, it is not just history written in microwaves. It is something the universe is doing now, and it is doing it to us, whether we notice or not. Still, the conservative interpretation remains strong, and it has grown stronger with better data and stricter analysis culture. Most of our motion can be attributed to known structures when surveys are deep enough, and reconstructions are careful about bias and completeness. The Great Attractor becomes a region within a larger basin, and Shapley becomes a major contributor that absorbs some of the mystery. The mystery shrinks, but it does not vanish, and shrinking mysteries can still cut. The dipole repeller reframes the same motion without requiring external physics, and that reframing is both elegant and unsettling. Voids and overdensities together can reproduce the observed dipole direction, at least within uncertainties that are honestly reported. In that view, the cosmos is strange but self-contained, and the apparent steering is just the web doing what the web does. The repeller is not a new entity, but a new way of describing the map, and maps change what we think we see. But the unresolved part is where the documentary lives, because the maps are still being refined and the catalogues are still growing. Bulk flow measurements still vary by method and sample, and the differences are not always trivial or easily dismissed. Some analyses find modest flows consistent with LCDM, and some report tensions that refuse to settle even after corrections. The question becomes whether the tensions are physics or bookkeeping, and how long we can tolerate ambiguity. We keep the case file open with clear standards because mystery without standards becomes mythology, and mythology is not a measurement. A real beyond-horizon tide should appear consistently across independent KSZ analyses, peculiar velocity reconstructions, and CMB large-scale modes, even when pipelines change. It should also predict correlations that can be tested with future surveys, rather than retrofitted explanations that only work backward. If it is real, it should leave fingerprints in more than one place, and the fingerprints should match. If those correlations fail, dark flow becomes a cautionary tale about extracting tiny signals from a loud sky, and about how desire can shape statistics. It becomes a lesson in how filtering, masking, and selection can manufacture coherence, and how a compelling phrase can outrun its uncertainties. If they succeed, the implication is heavier than any single cold spot, because it changes the boundary conditions of our universe. It would suggest our observable universe sits in a larger gravitational environment, like a bay inside a wider ocean. That environment could be ordinary structure beyond our horizon, or it could be another reality in a deeper sense, and the difference is not just philosophy. Either way, it would mean the cosmological principle is only approximately true, and approximation has a scale. It would mean isotropy is a local convenience, not a global law, and it would force us to ask what else we have mistaken for neutrality. When the universe has a current, even stillness becomes suspicious. This chapter ends with a bridge, because motion leads back to geometry. If something can tug us from beyond what we can see, it can also leave early imprints, and imprints are geometric as well as thermal. A tide today hints at contact yesterday, and contact leaves marks that persist when forces fade. The current becomes a clue that points backward in time, toward the earliest surfaces we can observe. Next, we move from gravitational anomalies to geometric ones. We return to the CMB and ask whether the sky shows collision-like signatures, shapes that look less like statistics and more like impact. If the universe is being pulled, we must ask what it hit, and whether the hit left a pattern we can recognize. So we set rules before we chase dangerous ideas. Then we follow the current, because the current might be the clue that spreads. This chapter ends with a bridge, because motion leads back to geometry. In cosmology, motion is often a bookkeeping choice. What matters is the shape of space-time itself, and how that shape guides every path. When we say the universe expands, we are naming a change in distance rules, not a wind that pushes galaxies outward. If the cosmos has a current, a preferred flow of expansion, it may also have an impact site, some place where geometry remembers a past encounter. We enter the multiverse in a disciplined way, because the word invites sloppy thinking. Multiverse can mean many things in popular culture, from parallel timelines to science fiction mirrors, yet here it points to a specific dynamical mechanism. Eternal inflation is not a slogan, and it is not a free pass to speculation. It is a class of models with calculable consequences. The discipline matters because the data are unforgiving, and the sky does not care about our metaphors. Inflation begins with a high-energy state that behaves like a false vacuum. In field theory language, a scalar field sits in a metastable minimum of its potential energy, like a ball resting in a shallow dip. The key is that this state has negative pressure, so it drives accelerated expansion through Einstein's equations. Its energy density stays nearly constant while space expands exponentially. And that near constancy is what makes inflation such a powerful smoothing mechanism. That expansion is not matter flying outward, it is the metric stretching. Distances grow because the scale factor changes, even when galaxies are not moving through space in the ordinary sense. The distinction is subtle but essential. Relativity allows space itself to expand without any object locally outrunning light. In many potentials, quantum fluctuations keep some regions inflating longer than others, because the field does not roll down identically everywhere. Those fluctuations are not decorative noise, they are the same quantum seeds that later become structure. During inflation, microscopic modes are stretched beyond the horizon, and their amplitudes effectively freeze, becoming classical perturbations in practice. The freezing is not mystical. It is a consequence of causal disconnection, because the mode's wavelength becomes larger than the region that can communicate. Some regions fluctuate uphill in the potential, so inflation persists there longer, and the local end time of inflation becomes a patchwork. The result can be self-reproduction, where inflation never ends everywhere at once. The background volume grows so fast that rare upward fluctuations still occur somewhere, at every moment, even if they are improbable in any one patch. This is the core of eternal inflation. Expansion creates more opportunities for fluctuations than decay removes. It ends locally, creating pocket regions that thermalize into hot Big Bang conditions, while the parent spacetime keeps inflating elsewhere. In visuals, the inflating background is a dark, swelling ocean of spacetime, featureless, relentless, and cold, with no stars because ordinary matter has not been made yet. The camera drifts through a black geometry that seems to breathe, as distances stretch faster than the intuition can follow. Then, like sparks in a fog, pockets ignite where the field rolls down and reheats, turning vacuum-like energy into a seething bath of particles. Those sparks are not explosions into space, they are new regions of hot, dense plasma forming inside an already expanding geometry. Those pockets are called bubble universes in the simplest picture. They nucleate like phase transitions, with a wall separating the new vacuum from the old, and the language is borrowed from condensed matter for a reason. The analogy is familiar, steam bubbles in boiling water, yet the physics is relativistic and quantum, and the boiling is a decay of a metastable vacuum. Historically, this picture grew from work on vacuum decay and instantons, where the probability of tunneling can be computed using semi-classical methods. In the thin wall approximation, the bubble wall is a narrow region where the field transitions between vacua. Its tension and the vacuum energy difference set the bubble's initial radius and acceleration, and they also control how much energy is stored in gradients. The wall is not a material shell, but it carries energy and therefore gravitates, so it bends space-time as it moves. In many models, the wall quickly becomes highly relativistic, racing outward through the parent inflating space. Inside a bubble, expansion slows into standard cosmology, and structure can form. Reheating converts vacuum-like energy into particles, radiation, and eventually atoms, and the details of reheating shape the initial conditions for the hot Big Bang. Temperatures soar, then fall, and the plasma cools through familiar milestones: nucleosynthesis, recombination, and the release of the cosmic microwave background. Outside, the inflating background keeps growing, separating bubbles faster than light can cross, so most bubbles never meet. That faster-than-light separation is not a violation of relativity, because it is the expansion of space itself. No signal outruns a local light beam in its own neighbourhood, and every observer still measures light moving at sea nearby. Yet horizons form, and causal contact becomes a precious limited resource, an accounting of what can influence what. The horizon is not a wall you can touch, but it is a boundary written into the geometry. Collisions are not fantasy in this framework because bubbles form in a shared inflating spacetime. If nucleation events occur close enough in the parent space, their future light cones intersect and the walls must interact. Geometry, not imagination, decides whether two bubbles meet, because the intersection is a spacetime fact. In many scenarios, the collision is rare, but rarity is not impossibility, and the sky is large. A collision perturbs fields and geometry at the bubble wall. The event is violent in the field theory sense: sharp gradients, energy transfer, and a sudden reshaping of curvature, all happening at relativistic speeds. The disturbance can propagate inward as a perturbation to the density and gravitational potential, and it can imprint the last scattering surface we observe as the CMB. The point is not that we see the wall itself, but that we might see its after effects in the oldest light. To picture it, imagine the bubble interior as a vast cooling sphere of plasma, glowing softly before atoms form. Now add a distant bruise on that sphere, an expanding disturbance that reaches the surface, where photons decouple and begin free flight. The CMB becomes a screen, and the collision becomes a pattern on that screen, preserved for billions of years. When NASA releases a full sky map, we are looking at a fossilized photograph of conditions at that surface. The key is falsifiability through predicted patterns, not metaphors about parallel worlds. A bubble collision should leave a localized azimuthally symmetric modulation on the sky, and the symmetry is not aesthetic. It comes from the approximate rotational symmetry around the collision axis. It is a specific kind of symmetry breaking with a calculable shape, and that shape can be encoded in a template. If a model cannot say what to look for, it is not yet a useful scientific claim. Azimuthally symmetric means the signal depends mainly on angular distance from a center. In temperature maps, it can look like a disk, sometimes with a sharp edge, and sometimes with a smoother fall-off that blends into the background. The center is not special in our coordinates. It is special because the physics picks it, like a scar's center on a surface. The disk is not expected to be perfectly clean, because it sits on top of ordinary primordial fluctuations. Theory templates often use a step-like or ramp-like profile across the disk. A step is closer to a sudden change at the boundary, while a ramp is a gradual gradient that slopes across the region. The amplitude and angular size depend on collision parameters and our location within the bubble, because observers at different positions would see different angular radii. Even the sign can vary, producing a hot or cold modulation, depending on how the collision perturbs the local potential. Those parameters include the vacuum energies, the wall tension, and the relative boost between bubbles, which sets the collision's kinematics. They also include when the collision occurs relative to our reheating and our last scattering, because timing controls how much the disturbance is diluted. A collision too early can be inflated away, while a collision too late can be too small to cover many degrees. The observable window is narrow enough to be interesting, and wide enough to be frustrating. The imprint is not expected to be a random hot or cold pixel. It is a coherent pattern that breaks statistical isotropy in a specific, testable way, and coherence is what makes it searchable. Coherence matters because it lets us separate a physical mechanism from random Gaussian fluctuations, at least in principle. In practice, the sky is a complicated mixture of signal, foregrounds, and instrument behavior. Polarization matters because it is a second channel tied to the same physics. CMB polarization arises from Thomson scattering, when radiation has a quadrupole anisotropy, meaning the incoming light is hotter in some directions than others. At last scattering, electrons act like tiny antennas, imprinting a preferred orientation on the outgoing light. A primordial disturbance at last scattering should correlate with E-mode polarization in a predictable pattern, because it changes the local velocity and density fields. E-modes are the curl-free component of polarization, and they carry information about velocity fields and density perturbations. A collision-induced modulation changes the local conditions at last scattering, temperature, velocity, and gravitational potential, and those changes are linked through the same perturbation equations. That coupling should leave a connected signature in temperature and E-modes, not two unrelated curiosities. The promise is that polarization can confirm or contradict a temperature-based story. A late-time effect like ISW from a void should have weaker large-scale polarization correlation. The integrated Sachs Wolf effect is a gravitational redshift accumulated as photons cross evolving potentials, especially when dark energy causes potentials to decay. It changes temperature after last scattering, so it does not automatically produce matching polarization, because the polarization was mostly set earlier. That temporal separation is why polarization becomes such a sharp diagnostic. That difference becomes a lever for killing or strengthening the collision idea. If temperature shows a disk but polarization matches the wrong phase or amplitude, the primordial story weakens, because the channels are no longer consistent. If polarization lines up with the expected pattern, the case becomes harder to dismiss, because two independent observables agree. The lever is not perfect, but it is one of the cleanest tools we have. Collisions can also generate non-Gaussian statistics beyond the standard Gaussian random field. Standard inflation predicts nearly Gaussian primordial perturbations, with small, constrained deviations that arise from weak interactions and slow roll dynamics. A localized collision is inherently non-Gaussian because it adds a structured feature to an otherwise random field. The non-Gaussianity is not just a number, it is a shape in the statistics, tied to localization. The signal is localized so it can appear in higher point functions and anomaly tests. It can show up in the spectrum, in wavelet coefficients, or in specialized spot statistics that look for coherent patches. Yet detection is not automatic because the sky is noisy in complicated ways, and the noise is not always white. Foregrounds and scanning patterns can also create localized features that masquerade as physics. But non-Gaussianity is a crowded courtroom because many systematics and foregrounds can mimic it. Galactic dust, synchrotron emission, point sources, and scanning artifacts all leave patterns, and some of those patterns are stubborn. The point is not that non-Gaussian equals multiverse, but that it is measurable and therefore constrainable. A serious analysis must show that the feature behaves like the CMB across frequencies and pipelines. To search, analysts build templates, which are parameterized signal shapes predicted by a model. A template is not a picture, it is a mathematical pattern slid across the sky, and it is evaluated by a likelihood function. It encodes a hypothesis in a form that can be tested against data, including uncertainties and correlations. In a sense, the template is the bridge between theory's equations and the map's pixels. In practice, a template includes a center direction, an angular scale, and an amplitude. It may also include a profile parameter that chooses step-like versus ramp-like behavior, or a parameter controlling edge sharpness. The template is convolved with the instrument beam and compared to maps with realistic noise, because the telescope blurs the sky. Analysts also account for masks because the Milky Way forces us to cut out contaminated regions. Template matching asks a strict question at each position and scale. Does the data prefer a collision profile over pure LCDM plus noise and foreground residuals once we account for correlations between pixels? The comparison is not just visual, because human pattern recognition is famously overconfident, especially with mottled textures. The algorithm must do what the eye cannot: compute how surprising the match is under a null model. This is where Bayesian evidence enters, because the model has extra parameters. Bayesian methods penalize complexity, so a weak improvement in fit may not justify a new component, even if the feature looks compelling. In other words, the model must earn its freedom with predictive power, not with flexibility. The penalty is not philosophical, it is mathematical, and it is built into the evidence integral. Bayesian evidence integrates the likelihood over the allowed parameter volume. That integration automatically punishes templates that fit only in a tiny corner of parameter space, because most parameter choices would not match the data. It is a formal version of skepticism built into the mathematics, and it is especially important for anomaly hunting. Without that discipline, every map becomes a Rorschach test. Map opened the modern era of full-sky precision CMB maps. Its multi-frequency design helps separate the CMB from foregrounds, and its long mission stabilized systematics over years of scanning. Planck then improved sensitivity, angular resolution, and frequency coverage, tightening the net around anomalies and sharpening cosmological parameters. Historically, these missions turned the CMB from a qualitative glow into a quantitative laboratory. Planck's maps are not a single image, but a carefully assembled product of detectors, scanning strategies, and calibration pipelines. Each frequency channel sees the sky differently, and component separation combines them into CMB estimates using statistical methods that balance signal and contamination. That complexity is a strength, because it provides cross-checks, but it also creates places for subtle errors to hide. A disciplined search must therefore test robustness across multiple map products. Teams scanned WMAP and Planck temperature maps for disk-like features. They varied center position, angular radius and amplitude, then computed likelihood ratios or evidences, and they repeated the procedure under different masks. The search is computationally heavy, because the sky has many possible centers and scales, and each evaluation involves large covariance structures. In the background, the work is less glamorous than the headlines: rows of simulations, null tests, and pipeline validation. Some pipelines used needlets or wavelets to find localized departures from Gaussianity. Needlets act like band-limited magnifying glasses, isolating features at chosen angular scales while retaining decent localization on the sky. Others used explicit collision templates derived from thin wall approximations and perturbation theory, which connect directly to model parameters. The methodological diversity is valuable, because different tools fail in different ways. The headline result was not a clean detection. Planck found no compelling Bayesian evidence for bubble collisions in the simplest template families, and the posterior odds did not favor adding a collision component. The data did not demand an extra disk-like feature once LCDM and known systematics were accounted for. In a field built on precision, not demanded is a meaningful statement. Null results do not mean collisions are impossible, because parameter space is large. They mean that if collisions occurred, their imprints must be small, rare, or shaped differently than the simplest templates, perhaps because of more complex potentials or reheating dynamics. The absence of an obvious disk is itself a constraint on the underlying inflationary landscape. Constraints are how science narrows the strange into the specific. Limits depend on assumptions about the parent vacuum, nucleation rate, and the distribution of collision strengths. They also depend on how the bubble interior curvature and reheating behave, because those affect how perturbations propagate to Lahr scattering. A small change in these assumptions can shift what detectable means, and that is why papers often read like careful bookkeeping. The multiverse, if it exists, does not come with a single parameter set. There is also an observational subtlety that rarely makes it into casual summaries. Our sky is one realization, and cosmic variance dominates the largest angular scales, where there are only a few independent modes. Even a real collision can be partially masked by the ordinary randomness of primordial fluctuations, because chance can add or subtract from the signal. The universe does not give us repeated trials, so statistics always carries a shadow of humility. This is the testability problem in miniature, and it requires honesty. Eternal inflation can be mathematically productive while still being difficult to corner observationally, because some signatures live where cosmic variance is strongest. The models can generate clear signatures in principle, yet those signatures may hide below the noise floor of the universe itself. The mystery is not just whether collisions happen, but whether they can ever be cleanly seen. Yet the search is not empty, because it produces constraints that rule out regions of model space. It also clarifies what a real signature would have to look like, which reduces the room for post-hoc storytelling. Over time, the methodology becomes sharper, and the excuses become fewer, because null tests get more demanding. In science, even a negative result can be a map of where not to look. A credible collision signature must survive frequency checks across Planck channels. If the feature changes with frequency like dust or synchrotron, it is not primordial, because the CMB has a precise blackbody spectrum. It must survive alternate component separation pipelines and independent map-making choices, because a fragile feature is often a processing artifact. Robustness is not optional when the claim is extraordinary. It must also appear consistently in polarization, at least in the ways predicted by the same disturbance. If temperature shows a disk but polarization does not, the model takes damage, because the channels should be linked by the same physics. Consistency across channels is the difference between an anomaly and a discovery, and it is what keeps a space documentary tethered to reality. The cosmos is strange, but our standards must be stricter than our curiosity. Now we return to the most famous candidate, because it refuses to leave the narrative. The cold spot is a large, coherent temperature depression with an unusual profile, first emphasized in due map analyses and then revisited with Planck. It sits in the southern galactic hemisphere, like a bruise on the oldest light, and it persists across different datasets. Its persistence is why it remains a recurring character in this story. On screen, the cold spot is deceptively simple. A blue patch on a mottled map, surrounded by warmer tones and fine-grained speckle, yet its scale is what makes it unsettling, because it spans degrees of sky, far larger than typical hot and cold patches. It is not a small defect. It is a broad, organized departure from the expected texture. The eye senses a coherence that statistics must then interrogate. Earlier we followed the conservative lead first, the Eridanus supervoid and the ISW effect. A large underdensity can make photons lose less energy climbing out than they gained falling in, if the potential decays over time due to cosmic acceleration. That explanation can contribute, but it struggles to pay the full amplitude bill, especially if the void is not extreme enough. The conservative story is attractive because it stays within known structure formation. Part of the struggle is quantitative, not rhetorical. The standard LCDM ISW signal from typical voids is modest, and the cold spot's depth looks unusually strong compared with what many simulations produce. To match it, the void must be unusually large, unusually aligned, or accompanied by additional effects like a particular profile or compensation. Each added requirement narrows probability, and probability is the currency of cosmological inference. A bubble collision was proposed as an alternative because it naturally creates a localized disk-like modulation. The cold spot's scale and isolation made it a tempting match, because it resembles the kind of azimuthally symmetric feature the templates describe. The idea is not that the cold spot proves a multiverse, but that it is the right kind of shape to test. In a universe full of random patterns, shape is a clue we can formalize. In collision language, the cold spot could be the interior of a collision disk. The surrounding ring-like structure, sometimes discussed, could reflect the template edge behavior, especially in a step-like profile where the boundary is sharper. If the profile includes a transition, the boundary can look like a faint rim, though the rim itself is debated. The visual temptation is strong, which is exactly why discipline is required. But temptation is not evidence, and the cold spot is also a known trap for a posteriori reasoning. If we choose the template because we saw the spot, we inflate significance, because the choice was guided by the data. The look elsewhere effect turns curiosity into overconfidence, because many possible anomalies could have been selected. The honest question is not, does it look like a disk, but how often would something like this appear by chance? So the question becomes, what would strengthen the collision hypothesis in a disciplined way? The first requirement is a polarization pattern consistent with the same disk center and profile, including the expected temperature, E-mode correlation. It's not enough to see some polarization feature. It must match the predicted structure in phase and scale. A match would not be final proof, but it would be a rare kind of consistency. A second requirement is consistency with lensing and large-scale structure correlations. If a void dominates, lensing convergence and galaxy counts should correlate in the right direction, because less matter means weaker gravitational focusing. The sky should look emptier in that direction, and the gravitational lensing signal should reflect less mass along the line of sight. These are measurable expectations, and modern surveys make them increasingly testable. If a collision dominates, the correlation with local structure could be weaker or qualitatively different. The collision is primordial, so it is not caused by a late-time underdensity, even though later structure could still form on top of it. It could coexist with a void, but it should not require a particular void to be present in order to explain the temperature pattern. That distinction matters because it separates a late-time story from an early-time scar. Better void mapping is therefore a critical kill test. If surveys show no substantial underdensity along the line of sight, the void explanation weakens and the collision story gains room, because the late-time mechanism loses its main lever. The cold spot would then demand a more primordial accounting, or a reconsideration of statistical flukes. Either way, the mystery would shift toward the early universe. If surveys confirm a deep, extended underdensity with the right redshift distribution, the collision story becomes less necessary. The cold spot could then be mostly local plus cosmic variance, with the void doing some work and chance doing the rest. In that case, the mystery shifts from multiverse drama to the statistics of rare structures. That shift is not disappointing. It is how science often resolves strange observations. Polarization is the sharpest blade because it is harder for late-time structure to fake. A collision should imprint specific E-mode correlations tied to the temperature modulation, because both arise from conditions at last scattering. ISW, by contrast, is a late gravitational effect and does not naturally generate the same polarization signature, since it acts after polarization is set. The blade is sharp, but the data must be sharp too. Planck polarization has improved, but large angular scales remain difficult. Instrumental systematics, correlated noise, and foreground polarization complicate a clean verdict at the cold spot scale, and cleaning polarized dust is notoriously challenging. Even with careful processing, the lowest multipoles are fragile, and small residuals can sway conclusions. The result is an uncomfortable middle ground where hints exist but certainty does not. So the evidence remains suggestive but not decisive, which is the honest centre of this chapter. The cold spot can be narrated as a candidate, not as a confirmation, and that distinction protects the story from drifting into myth. It is a place where theory can touch data, but not yet a place where data has spoken clearly. In a cosmos measured by NASA missions and international collaborations, patience is part of rigor. Now we widen the lens to the cosmological principle, because collisions are not the only anomaly. The CMB has long-running tensions at the larger scales, where cosmic variance is harsh and the number of independent modes is small. These are the modes with the fewest independent samples, and therefore the loudest arguments, because each outlier carries more narrative weight. The danger is that we can mistake limited statistics for deep physics. Low multipoles show odd behavior in some analyses, including low quadrupole power compared with LCDM expectations. There are reported alignments between the quadrupole and octopole that look axis-like, sometimes called an axis of evil in the literature's more dramatic moments. When plotted, the preferred directions can seem to point in related ways, as if the sky has a subtle spine. The question is whether that spine is real, or a mirage produced by masks and chance. There is also hemispherical power asymmetry, where one half of the sky appears slightly more variable. The effect is often described as a dipolar modulation of power, as though the fluctuation amplitude is gently higher in one direction. These effects are debated because significance depends on masks and statistics, and the Milky Way complicates every large-scale measurement. A small change in analysis choices can move an anomaly from intriguing to ordinary. Some anomalies could be residual systematics from scanning, beams, or foreground subtraction. The CMB is extracted from a bright structured Milky Way, and subtraction is never perfect, especially for polarized emission. Others could be statistical flukes amplified by the look elsewhere effect, because we test many statistics and remember the most surprising. The honest posture is to treat anomalies as prompts for tests, not as conclusions. But if even a subset are real, they stress the assumption of statistical isotropy. They suggest our sky may not be a typical draw from a perfectly homogeneous, isotropic ensemble, at least not on the larger scales. The cosmological principle is not a law of nature, but it is the foundation under most inferences, from parameter estimation to simulation design. When that foundation wobbles, the whole structure of interpretation feels less secure. This is where dread builds through scale, because the evidence is not local. These are boundary condition crimes written across the entire sky, in the oldest light we can measure, and that makes them psychologically different from a local mystery. The unsettling part is not the size of the anomalies, but their placement at the edge of what we can test, where new data are hardest to obtain. What if the universe is not only stranger than we imagine, but stranger than we can sample? A dangerous idea here is not a monster in the solar system. It is the possibility that our observable universe is not a sealed container, and that initial conditions were influenced by something beyond our horizon. If that is true, then outside becomes part of the story, even if it is forever unvisited. The question becomes, what does it mean to infer a cosmos when the boundary conditions may have an external cause? Into that opening steps a more speculative framework, associated with Laura Massini-Houghton. The idea is entanglement at birth. Where our universe's initial state was not isolated even during inflation, it treats the inflating patch as a quantum system with an environment, not as a self-contained stage, and it asks what happens when you trace out degrees of freedom you cannot observe. In quantum language, ignoring the environment can leave effective terms in the reduced description. In this picture, the wave function of the inflating region is entangled with other branches or other bubble domains. Tracing out the rest leaves an effective influence on our initial conditions, potentially modifying the distribution of primordial perturbations. In plain terms, ignoring the rest of the multiverse can leave fingerprints in the statistics we measure, even if we never see another universe directly. The fingerprints would live where the CMB is most delicate, at low multipoles. The claim is not that we see other universes directly, but that we see their statistical pressure. Large-scale anomalies could be the residue of that entanglement, encoded in Lowell modes as suppressed power or unusual correlations. The emphasis is on subtle correlations and large-scale modulation, not on a single dramatic disk. It is a different kind of collision story, less like an impact crater, more like a boundary condition that never belongs solely to us. Such models aim to explain alignments, asymmetries, and unusual features without relying on a single collision disk. They try to turn vague multiverse talk into a set of modified predictions, such as altered power at the larger scales or specific correlation patterns. The ambition is to move from narrative to calculation, even if the calculation is hard and the priors are contentious. The question is whether the predictions become sharp enough to risk being wrong. The criticism is immediate and necessary, because the framework is hard to test cleanly. Many parameters and priors can be adjusted, and the risk of post-diction is high, especially when anomalies guide model tuning. If a model can explain any anomaly after the fact, it explains none in advance, and it becomes a story rather than a theory. The burden is to specify what should have been seen and what should not. Still, the value of the idea is methodological pressure. It asks whether the initial conditions we assume are too simple for a quantum cosmology with a larger environment, and whether our statistical assumptions are too classical. It also asks a deeper question. What does typical mean when the universe is a quantum system and our observation is one branch? Even if the answer is nothing new, the question forces clarity about what our models actually assume. NASA and the broader cosmology community treat this as speculative, not settled. The discipline is to keep it in the hypothesis box until it makes sharp, risky predictions and until independent datasets can test them. In science, mystery is cheap, but constraints are expensive because they require careful modelling and hard-won data. The cosmos offers endless strange ideas, but only a few survive contact with measurement. So we return to what the data can and cannot say. Planck's constraints on non-Gaussianity are tight for many shapes, which limits how wild primordial physics can be without leaving detectable higher point signatures. Many inflationary alternatives are already squeezed by these bounds, and that squeezing is a success of precision cosmology. The universe may be strange, but it is also surprisingly consistent. Planck's temperature map is also cosmic variance limited on large scales, which means more sensitivity will not create more independent modes. We cannot manufacture new skies to average over, and we cannot rerun cosmic history to get another sample. Progress must come from polarization, lensing, and cross-correlations, where new information still exists. The future is not only better maps, but better combinations of maps. Ground-based CMB experiments add high-resolution polarization and lensing maps. They do not replace Planck at the larger scales, but they improve the joint picture by tightening constraints on parameters that propagate into large-scale expectations. By measuring smaller angular scales precisely, they help anchor models that then constrain what is plausible at the larger scales. The result is a more interconnected inference, where one part of the spectrum disciplines another. Large galaxy surveys improve the late-time side of the equation. Better maps of voids, superclusters, and lensing potentials sharpen the ISW accounting for features like the cold spot, and they reduce the room for vague explanations. The goal is a consistent story that links photons, matter, and geometry across cosmic time. When the story is consistent, the universe feels less like a mystery and more like a system. If the cold spot is mostly ISW, we should see consistent signatures in the matter distribution and lensing. If it is primordial, we should see the right polarization correlations and weaker structure ties, because the cause predates galaxies. Each hypothesis predicts a different pattern of agreement across datasets, and that pattern is the real test. The test is not one statistic, but a network of constraints that must all fit. If it is a collision, we should see a disk-like pattern that matches a collision template in both channels. We should also see statistical consistency, with a population model, not a single celebrity anomaly, because the mechanism would not produce only one special case. A multiverse claim cannot rest on one famous patch of sky, no matter how photogenic it is. The cosmos does not certify theories with a single bruise. That last point matters because one spot can be a fluke. A collision scenario predicts a distribution of possible disks, even if most are too weak to detect, and that distribution should be consistent with the absence of many strong features. The sky should contain a rate and a strength distribution, not a lone exception that demands special pleading. The absence of a crowd is itself information. Planck's null results already imply that if collisions occur, they are rare or subtle in our sky. That keeps the multiverse door ajar, but it narrows the doorway, because the allowed parameter space shrinks. It also forces more careful model building, because anything could happen is not a prediction, and it is not a template. The strange must be made precise, or it remains only strange. The keyword weave is not decoration. It is a reminder of audience expectations and scientific limits. A space documentary can say NASA, cosmos, universe, mystery, time, strange, dangerous objects, and those words carry real emotional weight. But those words must remain tethered to what the data can and can't say, or the narration becomes a different genre. The discipline is part of the drama, because it is the difference between wonder and wishful thinking. But the dangerous objects here are not asteroids or black holes. They are hypotheses that can infect interpretation if we stop demanding templates, priors, and cross-checks, because the mind loves patterns too much. The danger is not impact energy, it is epistemic drift, where speculation quietly replaces inference. In cosmology, the most dangerous collision can be between a beautiful idea and insufficient evidence. We keep the central question in frame: do multiple independent lines of evidence indicate interaction with another reality? And what would that imply for physics and the cosmos, if it were true? If the answer ever becomes yes, it will arrive through consistency, not spectacle, and through a pattern that survives every attempt to kill it. That is how extraordinary claims earn their place. In this chapter, the answer is not yes, and it is not no. The answer is that inflationary collisions are calculable, searchable, and still unconfirmed, and that is already a remarkable state of affairs. The framework is scientific precisely because it can be constrained, and it has been, by missions that turned the sky into a dataset. The multiverse, if it is more than a story, must live inside those constraints. The cold spot remains a candidate because it is coherent, persistent across missions, and hard to fully explain locally, yet it has not met the burden of a decisive collision signature, especially in polarization, where the verdict is still blurred by difficulty. Its meaning remains suspended between statistics, structure, and primordial physics, and that suspension is honest. The mystery remains, but it is a bounded mystery. The cosmological principle remains the default because it works astonishingly well, but it is under stress at the larger scales, where anomalies cluster and interpretation is fragile, and where cosmic variance limits our leverage. The universe looks simple on average, yet it may be whispering complexity at the edges, where our tests are weakest. The whisper could be physics or it could be chance, and the difference is hard. The dread comes from the possibility that these are not independent quirks. They could be related scars from outside our domain, or they could be the universe teaching us humility about statistics, because one sky is not a large sample. Either way, the oldest light is still capable of surprising us, and surprise is the engine of better questions. What exactly would it take to convince us that the boundary conditions were not self-contained? Next, we move from inflationary bubbles to a different kind of collision story. If impacts can happen in an inflating background, higher dimensional models ask a darker question, one that shifts the stage itself. What if the Big Bang itself was an impact? A brain collision in extra dimensions? And what if our hot beginning was the aftermath of geometry meeting geometry? The idea is speculative, but it stays on the same theme. Collisions as signatures written into space-time. If so, the oldest light might not just show ripples from our birth, but bruises from a boundary we cannot see. The CMB would become not only a relic of a hot beginning, but a diagnostic of the geometry that made that beginning possible, and of the rules that shaped it. So we set rules before we chase dangerous ideas, then we chase the next collision, because the geometry may be where the leak spreads. This chapter ends with a bridge, because collision stories can be deeper than bubbles. If the Big Bang was an impact, the impact might have happened off our stage, outside the coordinates we instinctively call space. On screen, the cosmos looks calm, black space, faint galaxies, a soft afterglow painted across the sky. Yet the calm can be deceptive, because the larger structures may remember forces that never lived entirely inside our familiar 3 dimensions. We have been hunting anomalies in the CMB and in large-scale motion, and we have treated them like clues left in snow. Now we ask what kind of architecture could make an outside influence physically plausible, without turning physics into a fairy tale. String theory begins as a repair job for quantum physics and gravity, and that origin matters for the tone of the idea. In the middle of the 20th century, physicists learned to quantize fields with extraordinary success, yet gravity resisted the same treatment. Quantum electrodynamics could be renormalized with disciplined bookkeeping, and its predictions matched experiments to absurd precision. When you try to quantize gravity the usual way, infinities pile up faster than you can renormalize them, and predictions lose meaning. The problem is not a missing trick, but a deeper mismatch between point particles and spacetime itself. String theory changes the starting point by replacing point particles with one-dimensional objects, and that replacement softens violent short-distance behavior. Interactions smear out over a tiny length scale, often imagined near the Planck length, so the math stops exploding quite so quickly. The string's finite size acts like a built-in ultraviolet filter, which is a plain language way of saying the theory avoids some catastrophic infinities. Even better, one vibration mode of the string behaves exactly like a graviton, so gravity is not added by hand. It emerges as one of the notes the string can play. When you quantize a relativistic string, mathematical consistency forces extra dimensions into the universe. This is not an artistic preference, and it is not a decorative flourish for science fiction. It is a demand imposed by symmetry, by the requirement that the theory keep its internal promises. In ordinary 4-dimensional space-time, the equations develop fatal inconsistencies, including anomalies that break gauge symmetry and destabilize the quantum theory. In higher dimensions, the theory cancels anomalies and keeps causality and unitarity intact, which is a plain language way of saying it still predicts probabilities that add up. The number of dimensions depends on the version of the theory, and each version carries a different technical story. Superstring theories live naturally in 10 dimensions, where supersymmetry pairs bosons and fermions in a way that tames certain divergences. Supersymmetry is not just a new cast of particles, it is a structural constraint that makes quantum corrections behave. M-theory suggests an 11-dimensional framework, which emerged in the 1990s as physicists noticed that 5 apparently different superstring theories were secretly related. That historical moment matters because it shifted extra dimensions from a quirky option to a unifying map. Dualities, mathematical equivalences between seemingly different theories, hinted that the landscape was one structure seen from different angles. The map did not prove the territory exists, but it showed that the mathematics wants a larger stage. Extra dimensions sound like fantasy until you remember how physics uses hidden directions. A wire looks one-dimensional from far away, yet it has a circular thickness that matters. From across a room, you can describe it as a line, but at the scale of an ant it becomes a cylinder with a surface. The key is that dimension is partly about what motions are available to you at a given energy. If the energy is too low, a direction can be real and still be effectively invisible. In astronomy, we already accept this logic when we infer unseen structures from their gravitational pull. Compactification is the standard move that hides those extra directions, and it comes with a specific geometric intuition. The extra dimensions are curled up into tiny shapes, so motion along them is hard to excite. In quantum mechanics, excitations cost energy, and small circles demand high momentum to wrap around them. That means the first excited modes can sit far beyond the reach of our accelerators, even if the dimensions are physically present. In field language, you get Kaluza, Klein towers, heavier copies of particles that would only appear if we could pump in enough energy. Small does not mean irrelevant, because geometry controls the spectrum of allowed vibrations. The shape of compact dimensions sets particle properties, couplings, and symmetry breaking, and it does so with the precision of a musical instrument. Change the geometry, and you change the harmonics. In this view, what we call particles are vibration modes of strings, and the same underlying object can appear as many different species. Different modes look like different masses and charges in our four-dimensional effective universe, because the extra-dimensional pattern sets the effective constants we measure. Even the number of particle families in some constructions can trace back to topological features of the compact space. If we could visualize this, we might see a tight, intricate origami folded into every point of space. The folds would be smaller than atoms by an absurd margin, yet their angles would decide whether electrons exist at all. That is a strange thought, and it is also a disciplined one because it translates laws into boundary conditions. It says the laws we observe might be shadows of deeper constraints that are geometric, not arbitrary. It also raises an uncomfortable question. If geometry sets the rules, how many different geometries are possible, and how many different physics could follow? And if many are possible, why do we see this one, this particular cosmos, with these particular symmetries? The theory also predicts extended objects beyond strings, and this is where the narrative begins to touch cosmology. Brains are membranes of various dimensions, and they can host fields the way a surface hosts waves. A one brain is like a string, a two brain is like a sheet, and higher brains extend into more directions. In many constructions, open strings end on brains, and their endpoints carry charges. That technical detail becomes a cosmological metaphor with teeth, because it suggests that entire families of particles could be confined to a brain by the way strings are allowed to attach. The confinement is not a prison wall, it is a rule about what kinds of strings can exist. Brain cosmology takes that idea seriously as a model of our cosmos. Our observable universe could be a three-dimensional brain embedded in a higher dimensional bulk, where the bulk is the full space that includes the extra dimensions. On screen, imagine a luminous film floating in darkness, with galaxies embedded like glitter in resin. The film is not floating inside ordinary space, because the bulk is not a room you could enter. The bulk is the larger geometry in which room is defined, and the brain is one surface inside that definition. The standard model fits naturally as brain-confined physics, and that confinement is not just a storytelling convenience. Gauge fields and charged matter can be stuck to the brain, unable to wander into the bulk, because their underlying strings have endpoints anchored to the brain. This anchoring can protect the consistency of particle physics while still allowing a larger arena. It also explains why we do not see electrons drifting into some invisible direction. They cannot because the rules that define them are tied to the brain itself, like ink that cannot lift off the page. Gravity is different because it is geometry itself, and geometry does not respect the same confinement. In many brain scenarios, gravitons can propagate in the bulk, spreading their influence across extra dimensions. That statement can be pictured as ripples leaving the film and travelling through the dark volume around it. The ripples still affect the film, but they are not trapped there, and the bulk becomes part of the gravitational circuit. That difference offers an intuitive reason gravity is weak, and the intuition is almost classical. If gravity leaks into extra dimensions, its field lines dilute, so the force looks faint on the brain. In a three-dimensional world, the inverse square law comes from field lines spreading over the surface of a sphere. Add extra dimensions, and the spreading happens faster, so the same source looks weaker when measured along the brain. This is not a claim that gravity is simple because gravity is the hardest force we have. It is a claim that gravity might be telling us the universe has more room than we can see, more directions for influence to disperse. The idea has a measurable edge because it changes Newton's law at short distances. If an extra dimension is large enough, gravity could deviate from inverse square below some scale, because the field lines would begin to explore the hidden direction. The deviation would not be dramatic at human scales, or we would have noticed it in bridges and buildings. It would show up only when distances become comparable to the size or curvature scale of the extra dimension. That is why laboratory tests of gravity, which sound humble, become cosmic tests of geometry. Experiments have tested gravity down to sub-millimeter ranges with torsion balances, and the setup is both delicate and brutal. A suspended mass twists under tiny forces, and the experimenters spend years chasing vibrations, temperature gradients, and electromagnetic contamination. On screen, we see gold-coated disks, vacuum chambers, and laser readouts trembling like a seismograph. We see the quiet heroism of null results. Months of stability to say, nothing unusual happened. So far, Newton holds, which constrains how large and how accessible extra dimensions can be. Constraints do not kill the idea, they shape it. And this is where the bulk becomes a design space. The bulk can be warped, curved, or structured so that gravity behaves normally until very small scales. Warped extra dimensions change the story without changing the data we already trust. In warped models, gravity can be localized near our brain even if the extra dimension is not tiny, because space-time curvature can act like a gravitational trap. The warp factor becomes a kind of lens, one that focuses gravity near us while letting the larger bulk remain mostly hidden. Historically, this was a turning point for the extra dimensions conversation. Early Kaluza, Klein ideas in the 1920s, tried to unify gravity and electromagnetism by adding a fifth dimension, and they already used compactification as a hiding place. Their ambition was elegant, even if the full standard model was still decades away. Later, string theory revived the strategy with far more mathematical machinery, and with quantum consistency as the driver. Then warped brain-world models showed that small is not the only way to hide a dimension. Curvature can hide it too, and curvature is gravity's native language. This is where the title becomes literal in a careful way. A neighbouring brain could be separated by a small distance in an extra dimension, even if it is unreachable in our space. Millimeters away does not mean a nearby star system, and it does not mean a secret planet behind Pluto. It means separation along a direction we cannot step into, because our matter is confined to the brain. The phrase is meant to be unsettling, but it must also be precise, because precision is what keeps strange ideas from turning dangerous. Two sheets can be close in a higher dimensional stack, while never intersecting in three-dimensional experience. The closeness is geometric, not navigational, and that distinction prevents nonsense. On screen, imagine two translucent layers of glass, almost touching, with patterns etched on each surface. From within one layer, you can move north, south, east, and west, yet you cannot climb into the gap. The gap exists, but your world does not include the coordinate that reaches it, so the separation remains real and unreachable. If another brain exists, it could carry its own fields and its own time evolution. From our perspective, it would be another reality that shares the bulk but not our coordinates. It might have its own version of matter, its own radiation, and its own cosmic history, unfolding in parallel. That does not automatically mean it has stars or life, because those are additional requirements. It means only that the equations could allow a second arena, and that our universe might not be the only surface where physics can happen. The leak between realities would then be selective, and that selectivity is the entire scientific hinge. Gravity could couple the brains, and other interactions might remain trapped, depending on the model's rules. A leak can mean energy transfer through gravitational modes, which would look like a subtle imbalance in our cosmic bookkeeping. It can also mean topology changes, where the bulk geometry allows rare connections that look like violations of isolation. In the language of geometry, boundaries can sometimes rearrange, and rearrangements can leave scars, small deviations that persist long after the event. This is where the story shifts from a bruise to a framework. An anomaly stops being a one-off oddity and becomes a symptom of a larger stage. If the stage is larger, then the anomalies are not merely mistakes in our measurement. They are potential messages about what our measurements cannot directly see. The question becomes sharper. What would a larger stage do to the early universe, where small causes become huge effects, and where initial conditions become destiny? Brain-world models also offer a different origin story for the hot beginning, and the alternative is not casual. In ekpyrotic and cyclic cosmologies, the Big Bang is not the start of time. The word ekpyrotic comes from an ancient Stoic idea of a cosmic conflagration, and the name is chosen to suggest renewal through fire, yet the physics is not poetic, because it is built from equations of motion and energy conditions. The model has to specify what contracts, what dominates the energy density, and how the transition avoids catastrophic instabilities. The ekpyrotic picture replaces early rapid expansion with a slow contraction phase, and that reversal changes the logic of smoothing. During contraction, the universe becomes smooth and flat through dynamical attractor behavior, meaning that many different initial conditions converge toward the same outcome. The smoothing mechanism is not inflation's exponential stretching. It is a stiff equation of state that suppresses anisotropies and curvature as contraction proceeds. In plain terms, the universe becomes less wrinkled because the dynamics punish wrinkles, and because the dominant component grows in a way that overwhelms disorder. This point is subtle, and it deserves to be seen. In an inflationary montage, space balloons outward, and tiny quantum fluctuations get frozen into the sky. In an ekpyrotic montage, the universe slowly tightens, like a lens focusing, while dangerous anisotropies are damped by the dominance of a high-pressure component. The equations say that certain forms of energy density grow faster than curvature during contraction, so curvature becomes comparatively irrelevant. That is the attractor at work, and it is a different kind of cosmic housekeeping than inflation provides. Then comes the event that resets the temperature, and this is where the collision metaphor becomes literal again. A brain collision, or brain interaction, produces a hot, dense state that looks like a big bang from inside. In the simplest telling, two brains approach in the extra dimension. Their collision converts kinetic and potential energy into radiation and matter on the brain, and the conversion is the reheating that populates the universe with particles. The details are model-dependent because the interaction must avoid producing the wrong relics or the wrong spectrum of perturbations. On screen, we do not show a cartoon crash, because that would mislead. We show two vast surfaces, each carrying faint patterns, sliding toward one another through a dark, curved bulk. At the moment of interaction, light blooms along the surface, like a sunrise racing across an ocean. The bang is not a point in space, but a sudden change in state across an entire brain. The scale is what makes it eerie, an event that is everywhere at once, because everywhere is the brain. The universe after the collision expands and cools in the familiar way, and the standard milestones still matter. Nucleosynthesis still forges light elements in the first minutes, and recombination still releases the CMB after hundreds of thousands of years. The cosmic web still grows by gravitational instability, and galaxies still ignite. Yet the prehistory is different, and that difference is exactly what makes the model testable. A different prehistory should leave a different fingerprint, even if the later universe looks comfortingly familiar. Cyclic versions repeat the sequence, and repetition is both a promise and a problem. Expansion dilutes structure, then a slow contraction smooths again, then another collision reheats, and the cycle continues. The appeal is philosophical as well as physical, because it offers a cosmos without a single beginning. The danger is technical, because cycles must avoid accumulating entropy in a way that ruins the next round. The models attempt to manage that with mechanisms that dilute or reset entropy, but the accounting must be explicit. If the bookkeeping fails, the cycle becomes a one-time story wearing a repeating mask. These models aim to address the same puzzles inflation addresses, and the overlap is intentional. They want a smooth cosmos, nearly scale-invariant perturbations, and a mechanism for structure seeds. Comparison with inflation is not optional, because inflation is the benchmark. Inflation smooths by stretching space, and it predicts a spectrum of primordial perturbations sourced by quantum fluctuations of fields in a rapidly expanding background. It also offers a simple intuition: stretch the wrinkles until they look flat, then let gravity amplify the remaining tiny differences. Ekpyrotic models generate perturbations through different fields and different dynamics, and that difference is where the forensic work begins. They often rely on entropic perturbations that later convert to curvature perturbations, meaning that fluctuations in one field become fluctuations in the density of the universe. The conversion can happen through a bend in field space, or an interaction between components, and the details matter because they control what we observe. This is not a place for vague claims, because the sky is precise. Even a small mismatch in conversion efficiency can change non-Gaussianity, tilt, and the phase relationships between modes. The difference shows up in observables that are hard to fake. Primordial gravitational waves, spectral tilt, and non-Gaussianity become the forensic signatures. Each one is a different kind of memory, and each one is measured with different systematics. If the universe is a crime scene, these are different fingerprints on different surfaces. The hard part is that cosmic variance blurs the largest scales, so we need patience and multiple instruments to separate physics from statistical luck. Inflation often predicts a potentially detectable background of primordial tensor modes, which are gravitational waves generated by the expansion itself. The amplitude depends on the energy scale of inflation, so a detection would be a measurement of physics at energies far beyond any collider. Ekpyrotic scenarios typically predict very small tensor amplitudes at CMB scales, because slow contraction does not amplify tensor modes the same way. So B-mode polarization becomes a discriminator, and it becomes a target that motivates missions. The question is simple to say and hard to answer. Does the early universe ring like a drum, or does it stay nearly silent in tensors? A strong primordial B-mode detection would favour inflation-like physics, while a persistent null pushes attention toward alternatives. But the story is not binary, because inflation has many versions, and some of them also predict tiny tensors. That is why we need multiple tests that combine, and why cosmology has become a game of cross-consistency. A single measurement rarely closes a case, especially when the signal is faint and the foregrounds are bright. Spectral tilt is one of those tests, and it is a subtle one. The scalar power spectrum is not perfectly scale invariant, and its tilt encodes the dynamics of the early universe. A red tilt means slightly more power on large scales than small scales, and Planck has measured that tilt with impressive precision. Both inflation and ekpyrotic models can produce the observed red tilt, yet they do it with different parameter choices and different stability conditions. The details depend on potentials, fields, and conversion mechanisms that must be specified, not merely named. In a serious model, the tilt is not a slogan, it is a computed output. Non-Gaussianity is another stress test, because it probes whether fluctuations were simple and nearly random. In the simplest slow-roll inflation models, the perturbations are close to Gaussian, meaning their statistics are largely captured by a two-point function. Ekpyrotic conversion processes can produce distinctive non-Gaussian signatures that differ from simple slow-roll inflation, especially if the conversion is nonlinear. The bispectrum shape and amplitude become crucial, because different mechanisms generate different triangle patterns in Fourier space. Those patterns are like accents in a language, subtle but diagnostic when you learn how to listen. Local-type non-Gaussianity is especially constrained, and future limits can rule out wide ekpyrotic parameter regions. This is where space facts become unforgiving, because the universe does not negotiate with our preferences. If a model predicts a non-Gaussianity that is too large, it is not almost right. It is wrong. That harshness is part of the beauty, because it keeps the mystery honest, and it forces the theory to earn every claim. Primordial gravitational waves are not only about B-modes in the CMB, and it helps to widen the lens. They also affect large-scale structure through subtle correlations, and they could be probed by future detectors across frequencies. Different experiments listen to different bands, from nanohertz timing arrays to ground-based interferometers. The early universe signal is hard to extract, but the possibility forces us to think in a multi-messenger way. The sky can speak in more than one language, and sometimes it whispers in polarization while shouting in timing residuals. Now, we tie the theory back to the evidence thread. If higher dimensional interactions exist, what would they do to the CMB and the cosmic web? We have already treated the CMB anomalies as hints, but hints must be connected to mechanisms. A brain collision could leave large-scale features that resemble the anomalies we already discussed. It could imprint localized modulations, asymmetries, or unusual correlations, especially if the collision was not perfectly uniform across the brain. Even a slight gradient in collision timing could bias the largest modes, because the largest modes are the ones with the longest memory. A neighbouring brain could also act as an external gravitational source, and this is where the bulk becomes an active participant. Its mass energy could curve the bulk, creating tidal effects that project onto our brain as large-scale potentials. Those potentials could bias the largest CMB modes, because the largest modes are the easiest to push around. They could also influence large-scale flows, making motion look coherent in ways that strain simple LCDM expectations. The effect would not be a new force, but a new boundary condition, gravity responding to a geometry larger than our map. The key is that the signature would be subtle and global, not a dramatic stamp. A higher dimensional influence would not necessarily make a bright disk. It could make a gentle preferred direction. It might show up as alignments, hemispherical asymmetry, or correlations between temperature and polarization that are slightly off the standard expectation. These are the kinds of effects that make cosmologists argue late into the night, because they live near the boundary between signal and systematic error. The arguments are not a weakness, they are the method, skepticism as a tool for seeing clearly. It could also make a cold region more probable by changing initial conditions, and that returns us to the cold spot with new caution. The cold spot would then be a symptom of boundary conditions, not a single late-time void. That does not mean the cold spot is a portal, and it does not mean it is a guaranteed sign of a neighbour. It means only that an external modulation could tilt the odds toward rare features. The word rare is doing real work here, because rare events happen in large datasets even without new physics. Large-scale structure could carry the same fingerprint, and this is where the cosmic web becomes part of the forensic lab. If the initial perturbations were modulated, the distribution of voids and superclusters could show correlated anisotropy. On screen, we fly through a simulation. Filaments glow like nerve fibers, clusters burn like embers, and voids open like silent caverns. A global modulation would not rearrange every galaxy, but it could bias statistics across enormous volumes. The challenge is that we must separate a primordial bias from late-time astrophysical messiness, because galaxies are complicated storytellers. We should be careful about what evidence means here, because the temptation is to treat mystery as proof. A brain story earns credibility only if it predicts linked patterns across independent datasets. Temperature alone is not enough, because temperature maps can be fooled by foregrounds and cosmic variants. Polarization alone is not enough, because polarization is fragile and hard to measure. The strength is in the combination: temperature, E modes, B modes, lensing, and structure, all pointing in the same direction. When independent probes agree, the cosmos stops looking like a coincidence. This is where NASA and ESA missions become the lab bench. The CMB is not a pretty background, it is a precision dataset that can kill ideas. WMAP and Planck mapped temperature and polarization across the sky, and their maps are like atlases of the infant universe. Planck in particular measured the angular power spectrum with such precision that it turned cosmology into a parameter science. It set tight constraints on the scalar spectrum non-Gaussianity and many forms of anisotropy, and those constraints are now the walls of the room. Within those walls, any extra-dimensional story has to move carefully and compute honestly. On screen we watch the maps assemble from raw time-ordered data. We see scanning patterns, calibration sources, and the slow emergence of a sky that is not guessed but measured. The mottled colours are not artistic, they are microkelvin differences in temperature, encoded as a picture. Each pixel is a record of photons that last scattered when the universe was a hot plasma. In that plasma, electrons and protons trapped light like fog traps' headlights until recombination cleared the air. The afterglow is a photograph of conditions when the cosmos was young, and it is still the cleanest evidence we have. Ground-based telescopes extend the polarization reach, and they do it with engineering that borders on obsessive. Experiments like BICEP and the South Pole Telescope push sensitivity to B modes and lensing reconstruction, operating in cold, dry air where the atmosphere is less hostile. The Atacama Cosmology Telescope adds high-resolution maps that refine lensing and small-scale power. Together, these instruments cross-check systematics and sharpen limits, because no single instrument is trusted alone. In this kind of astronomy, distrust is not cynicism, it is quality control. Future missions aim to go further, and the motivation is not just curiosity. Lightbird is designed to target large-scale B modes from space, reducing atmospheric noise and improving control of foregrounds. CMBS-4 aims to combine multiple ground sites and massive detector counts. Its goal is deeper polarization maps and better delensing, which improves tensor constraints. These projects are not only about inflation, because any early universe model must pass through the same observational gate. If brains want to be more than elegant math, they must survive the same tests. Delensing matters because lensing creates B modes that mimic primordial ones, and the mimicry is precise enough to fool us. Large-scale structure bends the paths of CMB photons, converting some E-mode polarization into B modes. Removing lensing contamination is essential if we want to see a faint primordial signal, and the removal requires its own measurements. It is a layered inference, like reconstructing a scene through multiple panes of glass. Each pane adds distortion, and each distortion must be modelled before the original image can be trusted. Polarized dust is the other enemy, and it is not optional to mention it. Foreground cleaning sets the floor for any claim about early universe gravitational waves. Dust grains align with magnetic fields and emit polarized light, and that emission can masquerade as the signal we want. On screen, we see the Milky Way's filaments in polarized maps, beautiful and dangerous. So the brain story lives or dies by patterns that survive cleaning. A real signal must be frequency independent like the CMB and consistent across pipelines, not just impressive in one plot. Now we raise the narrative tension in a controlled way. If our universe is a membrane, then leaking reality becomes a physical mechanism, not a metaphor. A leak could be gravitational only, showing up as unexplained lensing or missing mass effects, because gravity is the one interaction most likely to cross the boundary. It could be energy exchange that alters expansion history in subtle ways, perhaps changing how we infer dark energy from distance measurements. It could also be a rare topological event that looks like a localized scar, because in some models brains can reconnect or interact, producing transient disturbances. The word rare matters again, because rare events are where models either become predictive or dissolve into storytelling. The danger is not that a neighbor brain sends monsters through a portal, because that is not how the equations speak. The danger is that our conservation laws might be effective, not absolute, within a larger bulk. Conservation laws are tied to symmetries, and symmetries depend on the full geometry. If the full geometry includes directions we do not access, then what looks conserved on the brain might be part of a larger conservation statement in the bulk. That is a strange thought, and it is also a disciplined one, because it turns metaphysics into geometry and asks for measurable consequences. If energy can move off-brain, then cosmological accounting changes, and the change would be subtle rather than theatrical. Dark energy and dark matter could partly reflect geometry and leakage, not only new particles. This does not eliminate particle explanations, and it does not excuse sloppy claims. It simply widens the space of mechanisms that could produce missing effects. The universe might be hiding its balance sheet in the extra dimensions, and we might be reading only the page that faces us. Black holes enter here as gravity-dominant objects that stress our understanding, and they do it with a kind of elegance. In some extra-dimensional models, black holes could behave differently at small scales because the shape of space-time near the horizon could feel the extra dimensions. Higher dimensional gravity changes horizon structure and evaporation rates in principle, and it changes the spectrum of possible black hole solutions. Observations constrain dramatic deviations because astrophysical black holes behave consistently with general relativity. Yet the concept keeps gravity as the messenger, because black holes are where gravity speaks loudest. If any place could reveal hidden directions, it would be where curvature becomes extreme and time itself slows near a boundary. On screen, we linger on a black hole's silhouette, the bright ring of an accretion flow and the slow dance of stars around an unseen mass. The visuals are familiar now, but the question remains dangerous. If extra dimensions exist, do they leave any imprint on the most extreme curvature we can observe? Or does the warping that hides the bulk also hide its influence, keeping the brain's gravity effectively four-dimensional, even at the edge of a horizon? The silence of black holes, if they are silent, becomes a kind of constraint. Time also becomes less secure in these frameworks, and the insecurity is conceptual rather than mystical. If the bulk has its own geometry, then what we call cosmic time could be a brain-based parameter. That does not mean time is an illusion, and it does not mean causality dissolves. It means the global structure might allow histories that are not captured by a single four-dimensional narrative. A clock built from brain-confined matter measures brain time, and that may not be the only time in the full geometry. What would it mean, in practical astronomy, if two brains shared gravity, but not the same natural slicing into past and future? We return to the central question with sharper language. Do anomalies plus theory suggest another reality is interacting with ours, and what would that imply? At this stage, theory provides plausible channels for interaction, and it provides a vocabulary that is mathematically coherent. It does not provide a confirmed detection, and it must not be narrated as one. The honest posture is to treat these models as hypotheses with specific consequences, not as secret truths. In science, the mystery is not the conclusion, it is the motivation. But theory changes what we consider possible, and possibility matters because it guides what we look for. A higher dimensional neighbour can be close in the only sense that matters, which is geometric separation in the bulk. If that neighbour exists, the spread could be quiet. It could be a slow drift in gravitational boundary conditions that biases our larger scales over cosmic time, leaving a preference that only appears when we average over the whole sky. That kind of influence would feel like a whisper, not a shout, and the cosmos is full of whispers that require careful instruments to hear. The evidence thread becomes a checklist because checklists protect us from romance. Look for correlated anomalies in temperature and polarization. Look for unusual large-scale alignments. Look for tensor constraints. Look for non-Gaussian shapes that match a specific mechanism. Look for consistency with large-scale structure and lensing, because a real leak should echo across probes. If the checklist fails, brains remain elegant mathematics without observational teeth. If the checklist succeeds, physics stops being a closed room, and the walls become a doorway. Now we set up the next door in the narrative. If gravity can leak, then matter could exist that we cannot see except through gravity. Dark sectors become more than particles in our universe. They could be mirror matter on a neighbouring brain, or hidden fields coupled through the bulk. The idea is not that we have found such a sector, but that the architecture makes it thinkable in a controlled way. It also reframes a familiar question in astronomy. When we say dark, are we naming a particle, or admitting a missing coordinate? A shadow biosphere is a speculative phrase, but the physics question is concrete. Could complex structures exist in a sector that barely touches ours? If chemistry and stability can occur with different fields, could life be a broader category than our brain-based instincts assume? Or would the weak coupling make complexity impossible, leaving the neighbour brain as a cold, silent ledger of mass energy? The question is provocative, and it remains constrained by what we can test, because speculation without constraints is just another kind of fiction. The next chapter follows that implication without losing discipline. We move from geometry to hidden matter, because the leak would first appear as missing mass. So we set rules before we chase dangerous ideas. Then we chase the millimeter to nowhere, because the cosmos may have neighbours we cannot reach. This chapter ends with a bridge, because geometry implies neighbours, and neighbours imply hidden mass. Dark matter enters as the most conservative, other reality we already live with, because it is inferred from gravity rather than imagination. It is not a metaphor because galaxies rotate too fast for visible mass to hold them together. When astronomers measure Doppler shifts across a spiral disk, the outer stars refuse to slow down. In spiral galaxies, outer stars orbit at nearly constant speed, where Newton predicts a drop once most mass lies inside the orbit. The simplest reading is extra gravitational pull from unseen matter in a halo, extending far beyond the bright stellar disk. Visually, the evidence looks almost too clean to be true. A rotation curve plot rises near the centre, then stays flat like a ruler pressed against the axis. Overlaid luminous mass models fall away, because starlight and gas thin out with radius. The gap between the curves is not an aesthetic choice, it is a missing term in the gravitational budget. Historically, this did not arrive as a single revelation, but as an accumulation of stubborn discrepancies. Fritz Zwicky in the 1930s noticed galaxy clusters moving as if bound by far more mass than they contained in stars. Decades later, Vera Rubin and collaborators mapped galaxy rotation with enough precision to make the mismatch unavoidable. The modern picture is more sophisticated than those early hints, yet the core tension remains the same. Clusters repeat the riddle at larger scale, and the accounting fails the same way even when we include hot plasma. Galaxy velocities inside clusters require more mass than stars and hot gas provide, or else the cluster would disperse. X-ray gas maps show pressure support that still demands deeper gravitational wells, because the gas temperature reflects the depth of the potential. The mismatch persists across methods, which is why it became a pillar, not a rumour. The visuals here are stark and physical. An X-ray image shows a glowing, diffuse atmosphere filling the cluster like fog in a bowl. Optical images show only scattered islands of galaxies, too sparse to explain the heat. When you translate that heat into mass, the numbers insist on something else, something heavy and unseen. Gravitational lensing makes the case harder to dismiss, because it measures mass by bending light rather than by counting objects. Weak lensing statistics map mass fluctuations across the sky without asking what the mass is, using tiny, coherent distortions in galaxy shapes. Strong lensing arcs in clusters reveal concentrated mass where luminous matter is insufficient, forming crescents and rings around invisible centers. In merging clusters, lensing peaks can separate from gas peaks, implying mass that does not behave like plasma. On screen, lensing feels like a visual confession from space-time. Background galaxies stretch into arcs, as if the image itself is being pulled toward a hidden weight. A mass map, reconstructed from shear patterns, blooms in false color where there is little light. The famous bullet-style collisions are especially unsettling because the brightest baryonic component lags behind while the lensing mass moves ahead. The cosmic microwave background adds early universe evidence that does not rely on galaxy modeling, and that timing matters. The CMB power spectrum encodes matter content through peak heights and positions. Like a fingerprint pressed into radiation, baryons raise odd peaks through compression, while dark matter deepens potentials without pressure, changing the oscillation pattern. The best fit model requires a dominant non-baryonic matter component, long before galaxies formed. This is where the documentary can slow down and let the sky speak. A full sky CMB map looks like mottled paint, yet the statistics are precise to parts per million. The peaks in the power spectrum are not decorative, they are calibrated relics of sound waves in primordial plasma. If you remove dark matter from the fit, the pattern breaks in ways that cannot be patched with ordinary atoms. Structure formation closes the loop, because dark matter acts as a gravitational scaffold that keeps its shape while baryons hesitate. In the early universe, radiation pressure prevents baryons from clumping efficiently, because photons drag on charged particles. Dark matter can start clustering earlier, seeding potential wells that baryons later fall into once the universe cools. Simulations with dark matter reproduce the cosmic web far better than baryons alone, including filaments, nodes, and the distribution of galaxy clusters. The cosmic web is a perfect visual metaphor that is also literal. Filaments stretch like luminous spider silk across hundreds of millions of light years, with voids in between that feel almost empty. In a simulation, you can watch density fluctuations grow from noise into architecture over cosmic time. The eerie part is that most of the scaffolding is dark, and the galaxies are only the frost on its edges. So we have facts that point to missing mass, but not to its identity. And that distinction is the documentary's hinge. We know its abundance in the cosmic budget, and we know it is cold, or at least not too hot, because hot dark matter would smear out small structure. We know it interacts weakly with light, or it would glow, absorb, or leave spectral fingerprints. We do not know its particle nature, its interactions, or whether it is even a particle. Even the word dark can mislead, because it sounds like a substance rather than a behavior. In practice, it means electromagnetically quiet, not metaphysically hidden. It means the universe has mass that does not form bright disks, does not radiate efficiently, and does not show up in telescopes except through gravity. That is already strange enough. The standard particle candidates were built to be found, and that is part of the tension that now hangs over the field. WIMPs were attractive because they naturally give the right relic density through thermal freeze-out, a neat coincidence called the WIMP miracle. Axions were attractive because they solve a separate strong CP problem while behaving like cold dark matter, especially when produced non-thermally. Yet direct detection experiments have pushed WIMP cross-sections down, and collider searches have not delivered a clean signal. The visual language of this search is industrial and patient. Underground detector halls sit behind meters of rock, with tanks of xenon or argon waiting for a single recoil. Plots fill with exclusion curves, each new run carving away another region of parameter space. The silence is not empty, but it is disciplined, and it forces theory to either adapt or narrow. Null results do not erase dark matter, they sharpen the question of what dark means in the first place. If it is not a simple weak-scale particle, it may live in a hidden sector where the familiar forces barely reach. A hidden sector is not a fantasy realm, it is a set of fields that barely couple to ours, possibly with its own gauge symmetries and matter content. Gravity couples to energy momentum, so it couples to every sector, whether we like it or not. Now we set rules before we chase dangerous ideas, because hidden sectors can become a dumping ground. The rule is that any extra sector must respect cosmology, particle constraints, and astrophysical observations, even when it is designed to be quiet. It must not spoil Big Bang nucleosynthesis, which is a precision clock for early expansion and particle content. It must not add too much radiation energy, which the CMB reads as extra relativistic degrees of freedom. There is a reason BBN carries such authority in this story. In the first few minutes, the universe was hot enough for nuclear reactions, yet simple enough to compute with controlled uncertainties. The neutron-to-proton ratio froze out as expansion outran weak interactions. Then helium formed rapidly once deuterium could survive. If you change the expansion rate, you change those outcomes, and the light elements remember. Mirror matter is a specific hidden sector idea with a clean motivation, and it arrives from symmetry rather than from desperation. The standard model violates parity in weak interactions, which means nature distinguishes left from right in a fundamental way. Mirror matter proposes parity is restored by duplicating the standard model in a mirror sector, so the full theory respects a deeper symmetry. Every particle has a mirror partner with opposite chirality assignments, making the full theory parity symmetric. The concept is easy to say and hard to fully absorb. It is not one new particle, but a parallel copy of electrons, quarks, photons, and forces, arranged so that what looks left-handed here looks right-handed there. In the mirror sector, mirror atoms would be stable for the same reasons ordinary atoms are stable. The mirror world would have its own chemistry, but its light would not be our light. In the simplest mirror model, mirror particles interact with mirror photons and mirror forces, so they can form bound states and radiate in their own spectrum. Ordinary and mirror sectors share gravity, so they share space-time and cosmic expansion, and they influence the same large-scale geometry. The sectors can be almost completely decoupled, which explains invisibility in ordinary telescopes and detectors. Yet almost is where the story becomes testable and dangerous, because tiny couplings can still leave measurable traces. Portal interactions are the narrow doors between sectors, and they can be tiny without being irrelevant over cosmic time. Kinetic mixing can couple ordinary photons to mirror photons through a small mixing parameter, effectively giving mirror-charged particles a faint millicharge in our sector. A Higgs portal can couple the Higgs field to a mirror Higgs, altering masses, mixing angles, and decay patterns. Neutrino portals can mix sterile or mirror neutrinos with ordinary ones, changing oscillation patterns in ways that experiments can constrain. The visuals here can be schematic and elegant. Two columns of particles mirror each other on screen, connected by thin, almost apologetic lines labelled mixing. The lines are narrow, yet they imply a bridge that cannot be fully removed if the theory permits it. A small coupling is not a small idea when it acts for billions of years. These portals are constrained, but not always excluded, and that ambiguity keeps mirror matter alive as a disciplined possibility. Kinetic mixing is limited by laboratory searches, astrophysical cooling, and cosmological effects, because even tiny charges can change plasmas. Higgs portal couplings are limited by Higgs signal strengths and invisible decay bounds, which the LHC measures with increasing precision. Neutrino portal effects are limited by oscillation data and cosmological neutrino constraints, because neutrinos shape both laboratory signals and early universe expansion. Mirror matter changes early universe thermodynamics, which is where BBN becomes a gatekeeper with sharp teeth. If the mirror sector has the same temperature as ours, it adds too much radiation, because mirror photons and mirror neutrinos behave like extra light species. Extra radiation speeds up expansion, changing neutron to proton freeze-out and altering helium abundance in a way that's hard to hide. Observed light element abundances restrict any extra energy density during nucleosynthesis, and they do it with uncomfortable clarity. So viable mirror models often require a colder mirror sector, and that requirement is not cosmetic. A lower mirror temperature reduces its radiation contribution and keeps BBN consistent, because energy density scales strongly with temperature. It also changes mirror recombination and mirror structure formation, shifting when mirror atoms form and when mirror photons decouple. That shift affects how mirror matter clusters, and whether it behaves like collisionless cold matter or something more complex. This is where mirror stops being a simple word and becomes a thermodynamic history. If the mirror sector is colder, it can recombine earlier, turning mirror baryons into neutral mirror atoms sooner. Neutral matter interacts less with mirror radiation, so it can fall into gravitational wells more efficiently. The timing of that decoupling can change small-scale structure in ways surveys might notice. The CMB expresses the same constraint in a different language through effective neutrino species, which compresses a lot of physics into one number. Extra relativistic degrees of freedom appear as higher NDF, changing damping tails and peak phases through altered expansion and diffusion lengths. Planck and other data constrain NF tightly, leaving limited room for a warm hidden bath that behaves like radiation. The allowed room depends on assumptions, but it is not large, and it is shrinking as systematics improve. Direct detection adds another layer of silence that shapes the narrative, because it tests portals at human scale. If mirror matter couples only gravitationally, it will not scatter in detectors, and null results are expected, not surprising. If kinetic mixing exists, mirror atoms could scatter via millicharge-like effects, producing low-energy recoils that careful experiments can seek. Experiments have not seen consistent signals, which pushes mixing parameters smaller or pushes masses into hard regions where backgrounds dominate. Astrophysical observations also constrain self-interactions because dark matter shapes halos over billions of years. Strong self-interactions can core out density cusps and alter cluster collisions, changing the internal structure of galaxies and the behavior of merging systems. Some self-interaction is not ruled out, and may even help small-scale tensions that appear in dwarf galaxies. But mirror matter with mirror electromagnetism can be too collisional unless its fraction, temperature or chemistry is tuned. This is where the story shifts from missing mass to hidden complexity. A mirror sector is not just a particle, it is an entire chemistry, complete with cooling channels and phase changes. Mirror electrons and mirror protons can form mirror atoms, mirror molecules, and mirror dust, with mirror photons carrying energy away. If it cools efficiently, it can form mirror stars, mirror planets, and mirror strange objects that do not emit ordinary light. Imagine the visuals, because they are almost unfairly evocative. A starfield fades, and a second starfield appears in negative space, traced only by gravitational influence. A simulated galaxy forms a dark disk that never shines, nested inside the luminous one like a shadow cast inward. The ordinary galaxy looks suddenly incomplete, as if we have only been seeing the surface layer. Now the dread becomes local, because the overlap could be here, on Earth, in the solar system, threaded through familiar places. If mirror matter shares our volume, it could pass through us with almost no interaction, like a wind that does not touch skin. Gravity would still bind it to Earth or the Sun if it loses energy somehow, and that somehow is the crucial bottleneck. The question becomes whether any mirror matter could accumulate in planetary bodies without revealing itself. Capture is not automatic because gravity alone does not dissipate energy efficiently for passing particles. To become bound, something must carry energy away, and that usually means scattering or radiation in some sector. If portals are tiny, capture rates can be vanishingly small, yet not strictly zero. Over geological time, even rare processes can become worth estimating. A shadow biosphere is the extreme edge of that idea, and it must be framed as speculation with bright warning labels. It proposes life based on hidden sector chemistry, evolving under mirror electromagnetic forces with its own biochemistry analogues. Such life would be invisible to ordinary light and ordinary biochemistry, because the photons and bonds are not ours. It would still gravitate, and it would still carry energy, which are the only unavoidable channels. The evidentiary bar is extraordinary, because extraordinary claims need independent, converging anomalies that survive hostile scrutiny. A shadow biosphere would require signals that cannot be explained by known geology, biology, or instrumentation, even after careful cross-checks. It would require reproducible patterns across locations and time, not one-off curiosities. It would require predictions that can be falsified, not just stories that can be adjusted when data disagrees. So what would count as a signal if we stay disciplined and treat this as physics rather than folklore? Unexplained heat flow could be one clue if energy is deposited or extracted through portal interactions, altering local thermal budgets. Gravity-only anomalies could be another clue, like small persistent mass discrepancies in local measurements that repeat across instruments. Unexplained geophysical effects could be candidates, but only after eliminating mundane causes like groundwater, tectonics, calibration drift and human activity. Astronomical effects would be cleaner, because the solar system is a controlled laboratory, compared to Earth's complexity and noise. Mirror matter in the solar system could alter planetary ephemerides through additional mass, shifting orbital elements by tiny but measurable amounts. It could create subtle perturbations in spacecraft trajectories, showing up as residual accelerations after modelling radiation pressure and outgassing. It could create gravitational lensing or occultation effects without visible counterparts, though the signals would be tiny and rare. Voyager and Voyager 2 become narrative anchors because they are our long baseline probes, and their longevity is part of their power. They have crossed the heliopause and sampled the boundary of the Sun's influence, where the solar wind yields to interstellar space. Their tracking data tests gravity and forces over huge distances and long time, which is exactly where small accelerations become legible. If hidden mass were clumped in the outer solar system, it could leave fingerprints in residuals, provided we model every conventional force with ruthless care. The visuals can lean into distance and time. A thin trajectory line extends past the planets, past the termination shock and into darkness, with tick marks labelled by year. Telemetry numbers scroll like a heartbeat, faint and persistent, as if the spacecraft is whispering across the solar system. Overlaid residual plots show how small errors accumulate, and how hard it is to claim a new force. Modern exploration keeps the story grounded, because the lab is not only deep space and heroic missions from the past. SpaceX launches remind us that space is not abstract. It is an engineered environment we repeatedly enter with increasing frequency. Reusable rockets change cadence, and cadence changes data volume, because more flights mean more tracking and more calibration opportunities. More missions mean more telemetry, more navigation solutions, and more chances to notice small anomalies that would be invisible in sparse data. But we must not pretend that every anomaly is a portal, because that is how misinformation grows and how science loses its footing. Internet space mystery culture thrives on strange objects and half-explained clips, especially when context is missing. Even the word riddle signals how quickly a puzzle becomes a meme, and how fast uncertainty turns into certainty online. The documentary must keep facts separate from vibes, even while using the vibes to motivate tests. Now we widen the lens again, because hidden sectors are cosmological, not just local, and their fingerprints accumulate across the sky. If a mirror sector exists, it changes the growth of structure through additional components, including mirror baryons and mirror radiation. It can introduce dark acoustic oscillations if mirror photons couple to mirror baryons, creating pressure waves in the dark plasma. Those oscillations can suppress small-scale power, leaving measurable changes in the matter-power spectrum. CMB anisotropies can also carry subtle fingerprints of extra sectors, even when those sectors are colder and harder to excite. Additional scattering in a dark sector can change gravitational potentials over time, modifying how photons climb out of wells. That alters the early integrated SACs, Wolf effect, and shifts peak structure in ways that are small but patterned. Even if the sector is colder, its matter content changes the timing of equality and the lensing potential that smooths the peaks. Large-scale structure surveys become the second half of the detector because they observe the late-time consequences of early physics. Galaxy clustering, weak lensing, and Lyman alpha forest probe the matter-power spectrum across scales, from megaparsecs down toward the edge of nonlinearity. If hidden sectors damp small-scale structure, the cutoff shape can be compared with data, looking for consistent suppression. The comparison is not perfect, because baryonic feedback complicates small scales, but the constraints are tightening as simulations and observations improve. Now the existential question sharpens, because overlap implies proximity without contact, and that feels like a violation of intuition. If two sectors occupy the same volume, why do we not constantly collide, heat up, and light up in obvious ways? The simplest answer is interaction strength, because without portals, only gravity couples them. Gravity is weak at particle scales, so matter streams through matter without friction, like two transparent fluids passing in the same container. That weakness is why the overlap can be stable, and why it can be terrifying, because it makes cohabitation plausible. If the only shared channel is gravity, then the sectors can ignore each other chemically and thermally. Yet they still share the same geometry, and geometry is not optional. The neighbour is next door, but the walls are made of coupling constants. Portal interactions complicate the calm, because even tiny couplings can accumulate over time or become relevant in dense environments. Kinetic mixing could allow rare scattering events that deposit energy in detectors or in planetary interiors, producing heat or ionization at low levels. Higgs portal couplings could allow mass mixing that changes decay rates in subtle ways, shifting branching ratios and lifetimes. The point is not that catastrophe is likely, but that the boundary is not guaranteed to be perfectly sealed. Decoherence adds another layer of separation that is often misunderstood, and it can be explained without mysticism. Quantum systems interacting weakly can remain effectively independent for long periods, because entanglement with different environments scrambles phase relations. If sectors have different interaction networks, their macroscopic states may not entangle in ways that produce observable interference in our instruments. That does not make them ghosts, it makes them dynamically isolated, except for gravity's universal bookkeeping. Gravity is the unavoidable channel, and that is where dread becomes physical rather than poetic. Gravity cannot be turned off, and it acts across all sectors, summing energy and momentum without asking for permission. If a hidden sector forms compact objects, their gravity can affect ours, even if their light cannot. If enough hidden mass accumulates in the wrong place, it could perturb orbits, tides, and long-term stability. We should be honest about scale, because most scenarios are not apocalyptic and do not belong to disaster fiction. The dark matter density near Earth is low, and its gravitational influence is already included in galactic dynamics as a smooth background. Local accumulation is limited by capture physics and by constraints from heat flow and seismic data, which leave little room for large hidden reservoirs. The nightmare is not a guaranteed event, it is the existence of an uncharted neighbour with unknown couplings. But the chapter is the climax because it reframes the central question in the most intimate way. Another reality does not need a visible portal in the sky, glowing like a doorway in science fiction. It can be co-located, threaded through our world, and detectable only through gravity and rare mixing. The leak, if it exists, could be quiet enough to evade casual observation and loud enough to shape cosmic history. Now we tie back to the documentary's opening hook, because the scar in the sky may not be alone as a clue. A bruise in the CMB could be a collision signature, or it could be a boundary condition, or it could be a statistical fluke that still teaches humility. Hidden sectors offer a different mechanism for outside influence that still lives inside physics, without breaking conservation laws. They turn the idea of a neighbour from geometry into matter, and matter is easier to test. So we set rules before we chase dangerous ideas, and we list the rules as constraints that keep the mystery honest. BBN limits extra energy density and forces hidden sectors to be cold or sparse, or else they rewrite the light elements. The CMB limits extra radiation and constrains dark scattering and dark acoustic features because it is sensitive to expansion and potentials. Direct detection limits portal couplings and pushes interactions towards silence, because detectors have become exquisitely quiet. Yet silence is not absence, and that is the unsettling lesson that keeps returning. The universe already contains a dominant component we cannot see directly, and we accept it because the data demands it. If that component is part of a richer hidden world, then our reality is not the full inventory of what exists. The terror is not supernatural, it is the possibility that we have been sharing space with an unseen ecology of mass. Now we bring the human-scale anchor back to Earth, because the question must touch lived reality to feel like more than cosmology. Earth's gravity field is mapped with extreme precision, and small anomalies are usually explained by geology, density variations, and ocean mass shifts. But precision mapping also means the baseline is strong, and deviations stand out when they persist. The solar system is our cleanest nearby testbed, because orbital mechanics is unforgiving and repeatable over time. We ask what a shadow biosphere would do, if it existed, without indulging the fantasy or letting the idea float free. It would need energy sources, and it would need stable structures in its own sector, because life is organized chemistry under constraints. It might cluster in mirror oceans, mirror soils, or mirror atmospheres that do not interact with ours, sharing volume but not contact. Its presence would be inferred only indirectly, through gravity or through portal-driven heat and scattering. We also ask what it would not do, because constraints are part of the story and part of the discipline. It would not easily exchange chemicals with us because chemistry is electromagnetic and the sectors do not share photons. It would not leave ordinary fossils, ordinary DNA, or ordinary microbes, because those are signatures of our sector's bonds. It would not be detected by cameras because mirror photons do not couple to our detectors without mixing, and mixing is constrained. That is why the search must be framed as physics, not paranormal investigation, and not as a hunt for strange objects in blurry footage. Look for unexplained energy deposition in low background detectors, where noise is quantified rather than argued about. Look for seasonal or directional modulation consistent with Earth's motion through a dark halo, which provides a predictable time signature. Look for gravitational anomalies that repeat across instruments and methods, because repetition is what turns mystery into measurement. The broader hidden sector program is already embedded in mainstream research, even if the language sounds like horror when narrated slowly. Experiments search for dark photons, millicharged particles, and exotic Higgs decays, because portals have concrete experimental handles. Cosmologists fit models with extra components and compare to CMB and structured data, because the sky is a laboratory with enormous baseline. The work is slow, and the slowness is the method, because premature certainty is the enemy. Now we escalate toward existential risk without claiming inevitability, because the tone is mysterious, not apocalyptic. If sectors overlap, then rare interactions could still be dangerous if they trigger chain reactions, but that requires specific conditions. A tiny portal could allow energy transfer under extreme conditions, like inside stars or near compact objects, where densities and temperatures are enormous. If hidden matter accumulates in stellar cores, it could alter evolution in constrained but meaningful ways, shifting lifetimes or cooling. Astrophysical constraints already limit many such scenarios, which is part of the relief that keeps the story from becoming pure dread. Stellar cooling bounds restrict new light particles and new interactions because stars would lose energy too efficiently. Supernova 1987A constrains energy loss channels that would have changed neutrino signals, and those neutrinos were observed. Neutron star stability constrains exotic accumulation and collapse mechanisms because the existence of old neutron stars is itself a data point. But constraints are not a full map, and the unknown remains large enough to be intellectually honest about fear. Hidden sectors can be heavy, cold, and nearly inert, leaving few astrophysical handles and few laboratory signatures. They can be structured in ways that mimic collisionless matter on large scales, hiding complexity behind averaged behaviour. The nightmare is not that physics breaks, it is that physics allows complexity we cannot easily observe. Now we connect hidden sectors back to leakage as a measurable fingerprint, because the documentary's hook demands testability. If hidden matter interacts gravitationally only, its main signature is the gravitational architecture of the cosmos, which we read through lensing, clustering, and the CMB. If hidden matter has additional interactions, those interactions can leave subtle imprints in anisotropies and power spectra, changing shapes rather than creating obvious new objects. The leak becomes something you infer statistically, not something you film directly. The leak becomes a statistical question, not a cinematic one, and that is both frustrating and powerful. Does the data prefer a universe with one matter sector or multiple, once we account for systematics and modelling choices? Do residual tensions in structure growth hint at additional components or interactions, or do they dissolve with better astrophysics? Are there consistent deviations across probes that point to the same hidden parameters, or are we seeing unrelated noise? This is where the chapter's mystery tightens into a test plan, and the plan is concrete even when the subject is invisible. Measure Neff and primordial abundances with better precision and better systematics control, because early universe physics is sensitive to extra sectors. Improve small-scale structure measurements while modelling baryonic feedback honestly, because galaxies are messy and can mimic new physics. Push direct detection and accelerator searches into new parameter space for portals, because the only way out of silence is to listen better. The solar system remains our nearest laboratory, and it keeps the tone grounded in engineering rather than myth. Track spacecraft with higher precision and model non-gravitational forces with ruthless care, because thermal recoil and radiation pressure can masquerade as new physics. Map planetary motions and asteroid belts for unexplained perturbations, because gravity integrates over time. Use time as an ally, because long baselines reveal tiny accelerations that short missions cannot see. We also acknowledge the psychological trap, because hidden sectors invite a certain kind of storytelling that can outrun evidence. When something is invisible, every gap becomes a place to hide a claim, and every strange object becomes a candidate explanation. The documentary must resist that drift, because the audience deserves a boundary between mystery and misinformation. The word riddle is a nod to the culture, not an endorsement of its shortcuts. Now we return to the central question at maximum tension, because the bridge from cosmology to intimacy is the chapter's point. If another reality interacts with ours, the most plausible channel is not a wormhole or a glowing tear. It is a dark sector sharing our space and our gravity, obeying the same geometry while refusing our light. The terrifying spread is not an invasion. It is the slow realization that the universe is not a sealed container, and if realities overlap, we ask the final practical question of this chapter, because practicality is where dread becomes measurable. What prevents catastrophic interaction is not goodwill, it is coupling strength and cosmic history, which set the conditions of contact. Gravity couples everything but rarely concentrates enough to cause sudden contact at human scale, and that is why life continues normally. Portals, if they exist, are constrained to be small, or we would already see their fingerprints in labs, stars, and the sky. So we end on a knife edge, because the data allows both comfort and dread without resolving the tension. Comfort says dark matter is inert, and we simply have not identified it yet, and that the universe is quiet. Dread says inert is not the same as empty, and a mirror world could be threaded through Earth and the solar system, complex but unseen. The facts support missing mass, and the mystery is what kind of missing it is. Now we set up the next door in the narrative, because hidden sectors are still only one kind of multiplicity allowed by physics. If physics allows parallel sectors in the same space, it also allows parallel branches in quantum measurement, coexisting without communication. The next chapter moves from hidden mass next door to hidden branches inside you. We move toward many worlds, quantum immortality, and the unsettling idea that you might be confined to a survivor timeline. So we set rules before we chase dangerous ideas, then we chase the last one, because the leak may not be in space alone. It may be in probability, in time, and in the way reality selects what continues. Now we widen the lens from scars in the sky to rules beneath the sky. Another reality may be embedded in quantum mechanics, not parked beyond our horizon. On screen, the universe looks calm, nebulae drifting, galaxies turning, yet the mathematics underneath keeps whispering that one outcome might be a convenient story. The many worlds interpretation says the wave function never collapses, it branches. In the standard equations, a quantum state evolves smoothly and reversibly, and MWI takes that literally. No special moment when nature chooses. Measurement becomes entanglement with an environment, and decoherence hides interference between branches. The detector, the air molecules, even stray photons become part of the bookkeeping, spreading phase information into degrees of freedom we cannot track. Decoherence explains why branches stop talking, not why one outcome feels selected. It turns a crisp superposition into a practical blur, because interference becomes astronomically hard to recover. MWI adds no new force, it relabels the same equations we already use. That is why its defenders call it conservative, yet its implications feel anything but. That distinction matters for a space documentary built on facts about space. MWI rarely changes predictions, because standard quantum mechanics already matches experiments with brutal precision. From atomic clocks to superconducting circuits, the numbers land with uncanny accuracy, and interpretations ride behind the data like shadows. Historically, this argument grew from the measurement problem itself, a debate that has followed quantum theory since the early 20th century. So we set rules before we chase dangerous ideas. Interpretation is not evidence, and philosophy is not a new particle. If an interpretation cannot be separated by an experiment, it lives in the realm of explanatory taste, not discovery. Still, taste matters, because the story we tell about reality shapes which questions we dare to ask. Quantum immortality rides on MWI as a thought experiment, not established science. If outcomes branch, you might only experience branches where you survive. The setup is simple and chilling. In a risky event with multiple outcomes, there exist branches where the observer continues, even if most branches end. The thought experiment borrows the cold logic of selection, then points it inward at consciousness. The horror is statistical, not supernatural, and it depends on assumptions about consciousness. It imagines awareness drifting into ever rarer survivor branches, where life continues but reality grows stranger. In those branches, survival may come with accumulating improbabilities, near misses, unlikely recoveries, a life that feels increasingly out of tune with ordinary expectation. What would it mean to keep going if the price is a world that looks normal, yet behaves like a rigged game. We should say what it does not prove, because the internet turns mystery into certainty. It does not show you cannot die, and it does not predict a testable escape from probability. It also does not explain what consciousness is, or how experience would track a particular branch. It is a mirror held up to our intuitions, asking whether we confuse "there exists a branch" with "I am guaranteed to be in it." Now we pivot from interpretation to a concrete cosmic risk written into field theory. Vacuum decay is not a metaphor, it is a possible phase transition of the cosmos. In quantum field theory, what we call empty space is not empty at all. It is a state with energy, structure, and rules encoded in fields. The vacuum is the baseline configuration of those fields, and baselines can be precarious. Our vacuum may be metastable, meaning it is not the lowest energy state. Like a ball resting in a shallow dip, it can persist for immense times, yet still be vulnerable. Quantum tunneling can nucleate a true vacuum bubble, even without any trigger. No asteroid is required, no warning flare, just a rare fluctuation that finds a lower energy arrangement. A nucleated bubble would expand at near light speed, converting space as it goes. The bubble wall is not a material surface, but a boundary between field configurations, and it would sweep outward with relativistic inevitability. Inside, particle masses and forces could change, and chemistry could fail instantly. Even the stability of atoms could be rewritten. Because the constants we treat as permanent may be properties of our current vacuum, there is no warning signal, because the wall outruns any message. The end would look like normal time, until physics itself becomes a different rulebook. On a visualization, the night sky stays serene. Then a silent front crosses the frame, and the familiar spectrum of matter simply stops making sense. Evidence status is measured, not cinematic. Higgs and top quark masses place us near a boundary between stable and metastable vacua. But uncertainties remain. Those masses feed into calculations of the Higgs potential at extremely high energies, where the curve may tilt toward instability. Yet the inputs have error bars, and the extrapolation assumes no new physics intervenes. That does not mean imminent doom, it means the risk is unknown. The standard model may be safe for times far beyond the age of the universe, or not. The calculated lifetime could be unimaginably long, making the danger practically irrelevant, or it could be shorter in ways we cannot yet constrain. The unsettling part is not a countdown clock, but the idea that the cosmos might sit on a ledge. Now we return to the collision thread, because cyclic ideas keep the impact story alive. In ekpyrotic or cyclic cosmology, a brain collision can be ancestral history. These models borrow language from higher dimensional theories, where our visible universe is a kind of surface, and cosmic evolution includes approaches and impacts. The Big Bang becomes less of a beginning and more of a transition. If the Big Bang was an impact, another reality is not hypothetical but prior. The cosmos could be a repeating sequence of approach, collision, reheating, and expansion. Each cycle would reset conditions while preserving a deeper continuity, like tides driven by dynamics we only glimpse. The question becomes unsettlingly practical. If there was a previous cycle, what traces could survive into ours? Now we bring back the anomaly board, because data is where dread earns its place. The cold spot persists, even as the supervoid explanation remains debated. On the board, it is a bruise in the microwave sky, a region where temperature dips beyond the simplest expectations. A supervoid could imprint such a feature through the integrated Sachs, Wolf effect. Yet the statistics and the structure surveys do not settle the argument cleanly. Large-scale flows and bulk motion claims strain simple expectations, though systematics still haunt them. When we map galaxy motions across enormous volumes, we are testing whether the universe is isotropic in practice, not just in principle. The Great Attractor and Dipole Repeller map a gravitational architecture that feels unfinished. They sketch a push and pull across hundreds of millions of light years, as if the local cosmos is being guided by structures we only partially chart. None of this proves a parallel universe collision, and that restraint is part of the method. Yet the tensions remind us the universe may be less isolated and less stable. If anomalies persist under better instruments, they become less like curiosities and more like boundary conditions, constraints that theory must obey. The next tests are specific and unromantic. Better polarization maps, better delensing, deeper surveys, and cross-correlated probes that can survive cosmic variance. Polarization, especially B modes, can separate primordial signals from foreground dust, and delensing can peel away distortions caused by intervening matter. Deeper galaxy catalogues can test voids and flows with cleaner statistics, tightening the leash on speculation. NASA and partner missions become the quiet protagonists of this ending. Satellites map the CMB, and deep space probes like Voyager keep reporting from the edge. In the visuals, antennas turn with patient precision, and data streams arrive as thin lines on dark screens, fragile evidence hauled across vast time. Even when the signals are mundane, the act of listening is profound. A black hole remains our metaphor for horizons and information, because boundaries shape what can be known. Event horizons hide interiors, and cosmological horizons hide beginnings, and both force us to confront what observable really means. The real mystery is whether reality has neighbours, and whether rules can flip. If the vacuum can change, and if cycles can recur, then the universe is less a container and more a process. Meaningful resolution is a careful answer to the central question. No single anomaly seals the case, but multiple cracks justify deeper theory and sharper observation. Science advances by refusing to confuse suggestive patterns with proof, while still admitting that patterns can be the first hint of a new framework. The terrifying spread is not an invasion from space. It is our expanding ability to detect boundary conditions. As instruments improve, the cosmos looks less like a sealed container. The more precisely we measure, the more we notice that smooth and simple are assumptions we must constantly re-earn. We end with fragile antennas pointed into time and darkness, listening for patterns that should not exist. The horror is not monsters, but physics admitting it has edges. And if it has edges, then somewhere beyond the last clean map, something else may be pressing back. We began with a bruise on the sky, the cold spot in the CMB, and followed the most conservative trail first. The Eridanus Supervoid could explain part of it, yet the numbers never quite close, and the sky keeps its unease. Then the story widened into motion, into claims of dark flow and lopsided large-scale pools, where geometry and gravity hint at structure beyond our cleanest maps. From there we tested bigger frameworks, bubble collisions, brains and bulk dimensions, and the unsettling possibility that an impact could happen off-stage, outside our familiar coordinates. We treated dark matter as the closest thing to an other reality we already accept, then asked if it is simple and silent, or a richer hidden sector like mirror matter with faint portal couplings. That question turns local and practical, because if hidden matter can pool near Earth, it should leave fingerprints in heat, gravity, or spacecraft trajectories, and if it cannot, the constraints become their own kind of evidence. Finally, we stepped beneath the sky into the rules themselves, where many worlds offers neighbours not in space but in measurement, and where vacuum decay reminds us that even a stable-looking universe may be only conditionally safe. Across every chapter, one lesson kept returning. Cosmic horror is not defeated by certainty, it is contained by disciplined tests and better instruments. The anomalies we traced could still be statistics, overlooked systematics, or the ordinary messiness of a lumpy universe seen through imperfect data. But if the cold spot, the debated void imprint, the large-scale flows, and the great attractor's strange bookkeeping survive polarization maps, delensing, deeper surveys, and cross-correlated probes, then leaking stops being a metaphor and becomes a boundary condition. In that case, cosmology would be forced to admit an interaction term, a neighbour sector, or a pre-inflationary scar, something that reaches us without asking permission. The terrifying part is not that another reality would be touching ours, it is that it might already be touching us so gently that we can only see it in the averages. So, are we watching another reality leak into ours, and is it spreading toward us? The most honest answer is that we do not yet know, and the more useful reframing is sharper. Our universe may not be a sealed container, and the seams are exactly where the data refuses to behave. If there is a neighbour, it will not announce itself with a doorway in the desert. It will appear as a persistent mismatch between independent measurements that should have agreed. What we call outside may be nothing more than the part of reality our current equations cannot yet hold, and the first sign of it is tension that will not wash away. If physics has a fate, it is to keep turning terror into geometry, and to keep asking whether the horizon is a